Hi, everybody. Let's go ahead and get started. I'm going to be talking about on-target iteration in Unreal Engine 5.5 and beyond. In terms of an introduction, my name is Osar Shaker. I'm a lead programmer on the Unreal Engine Foundation team. And I want to be clear as I'm presenting this material that this is not just like, hey, look at my work. Rather, this is the result of a lot of development effort by a lot of talented developers on the Unreal Engine team, spanning Foundation as well as consoles and other teams. I'm going to be going through a lot of material, so we're going to cover a lot of ground. If it feels like things are going fast, just know that in the end I will leave time for questions. And also I've got a link near the end of the presentation that will direct you to documentation, so you can find out more afterwards. So what we set out to do was improve content iteration speed on consoles and mobile. What we want is for content iteration on target platform to be closer in speed to what code iteration is like. I'm an engineer. When I need to make a change and see it on target platform, I have to go through a recompile process, and that takes time, but it's much less time than what a content creator has to go through when they want to see content changes on target platform. So we want to close the gap there. So what's involved in the current pipeline for content iteration? I'm going to focus on three specific phases: cook, stage, and deploy. There's other phases we could talk about: first-party packaging, boot and load time. Those exist. I'm not saying those don't matter. Just it's these three specific phases that I'm going to focus on. And they happen in that sequence: cook first, then stage, then deploy. So what's involved in each? Well, cook is the sometimes time-consuming process to load and save all the data in the game for a specific platform and store it as thousands of files in the saved cooked platform directory. From there, we do a stage, which copies the game executables, as well as those cooked output files that were produced from the first phase, and either store them as they were, thousands of files, only now copied over into the staged builds directory, or we can stage to container files. That's pack files or UCAS files that are aggregating that cooked data into fewer files, aggregating and sometimes compressing that cooked data into fewer files. But those also exist in the staged builds directory. And then finally, deploy. Relatively straightforward. It's just the act of taking the staged build and copying it over to our target platform, whether it's console or mobile device. And once it's there, it's ready for execution. So I'm going to be showing some diagrams with example data on them. I just want to note the data that I show is hypothetical. It's just meant to be representative of a current gen console game in terms of size and quantity. Every data set is different, but this is just an example. So one way to visualize this is as shown here. Starting with the cook phase, that is taking in UAsset files. It is also taking in files from the DDC or derived data cache. And then it is writing out cooked output files under the saved cooked platform directory. So in this example, hypothetically, let's say that produces 60 gigabytes of output spread across 1 million files. From there, we've got the stage phase. And the stage phase takes in the game executables, which are comparatively smaller and fewer, let's say 5 gigabytes in 4 files. And it takes in all of the cooked output files produced from the first stage, cook. So it has to read all of that back in, and then it has to write out the staged game. In this example, I'm staging to container files, which means I'm producing pack files, UTOCs and UCASs. And so you can see the relative proportion of the input and the output. So in this case, the output is 65 gigabytes of data spread across 80 files. We've taken those million files and aggregated them into much larger container or pack files. And then finally, deploy. Deploy, like I said, relatively straightforward. Taking the stage build, getting it over to the target device. So it's got to go from our workstation to a target platform, and that happens over either a network connection or a USB link in the case of mobile devices. So putting these together side by side, you can visualize it like this. So you can see cook, stage, deploy, and all the same as what we saw earlier, just strung together. So you can see how the output of cook is also fed in as the input of stage and onwards until we end up with a build on our target platform that's ready for execution. Okay, so what are the problems that can come up with this? Well, there's no shortage, especially as games get large. The cook can take 60 minutes or more. It has to load and save every file in a project. It repeats processing of files that haven't changed every time you cook. It's sensitive to DDC latency and hit rate, and it writes out thousands to millions of files. And also, it doesn't use multiple cores very efficiently. Stage can take 5 to 90 minutes, depending on compression. If you're doing a high level of compression, it's going to take longer. If you're doing no compression or a low level compression, it's going to be shorter. Lot of data getting copied around on disk during stage, and much of the work is actually irrelevant to a person iterating. It's not strictly necessary. And then when it comes to deploy, that can take 3 minutes or more. It tries to be smart by incrementally copying, that is copying only things that have changed. However, because we aggregate into container files, that somewhat undermines the incremental copy attempt that it does. So what we see is an outcome where content creators say, you want me to wait how long to see my work on target? And then they retreat to the relative comfort of Play in Editor or Pi. These problems aren't exclusive to content creators. These affect automated builds too, so there's more breadth to it than just the content creator workflow. So I'm going to start talking about steps we've taken that try and address or mitigate these issues. I'm going to start with stuff that's available in 5.4, then move on to stuff that's in 5.5, and then finally talk about future items in 5.6 and beyond. The first that I'm going to talk about is multiprocess cook. This has been production ready since UE 5.4, and for us within Epic, we saw a greater than 50% time reduction by applying it on Fortnite to our cook times on the build farm. We went from a single process cook to 4 process cook, and that reduced the cook time by over 50%. Critically, it has been reliable enough that Fortnite has been shipping with multiprocess cook. The builds that it produces and ships to users have been produced with multiprocess cook for the past 1.5 years. And our automated processes now use anywhere from 4 to 10 processes during cook, depending on how much RAM is available. It is critical to be aware that using multiprocess cook is a trade. You're trading memory for wall time reduction, and you need to make sure you've got enough memory to make that trade. So besides having memory, it's also critical that you allow page files on your machines to grow and span drives. One of the common problems we've seen is that page files are constrained to only be on the system drive, which may not be large, and so allowing it to span drives makes it feasible to use multiprocess cook. The other thing to be aware of is that by using more memory, we have more garbage collects that kick in response to low memory situations. This can surface latent issues that already exist in your build. If you have dangling pointers after garbage collect, you might have had few or no issues before, but because garbage collection is happening more frequently, those issues can surface when you start using multiprocess cook. But other than that, we've not seen other issues introduced by multiprocess cook, not determinism issues or anything of that nature. In terms of how to make use of multiprocess cook, we've tried to make it relatively straightforward. For your project, you can go into your default editor.ini in the cook settings section and set a cook process count that indicates how many processes you want the cook to use by default. You can also set another value that's your cook process from editor in case you want to use fewer processes to leave some memory space for the editor. And regardless of what you've set up in your config, any invocation of the cooker, you can always pass a command line argument, cook process count equals n, and that specifies how many processes you want the cooker to use. And then it takes care of everything from there, launching other cook processes and the inter-process communication that happens between them. Okay, so that was multi-process cook. I'm going to talk about Unreal Zen Server next. This is something that first started to show up for people in UE 5.4. I mean, it existed before, but it became a part of the default workflow in 5.4. You're going to hear me refer to it as Zen Server or Zen. It's the same thing, just shortened nomenclature. And what we're doing with it is we're using it to store data when the file system isn't scaling to our needs. It's tailored for content pipeline use cases, and the way the engine interacts with it is via network sockets. I'm going to talk about how it's applied in different roles. So you'll hear me say Zen as X, Zen as Y, as I go through this presentation. So just some foundational information about how it works. First thing you need to know is it's a separate process. So when you launch Unreal Editor or other UE tools, they will launch Zen Server on your machine as a separate process alongside them when they're using a feature that requires Zen Server. It is available for Windows, Mac, and Linux, so you'll find pre-built executables sitting in the engine binaries directory. And the Zen Server process services requests and provides responses over a network socket. We're using HTTP today, but that's an internal implementation detail that shouldn't be relied on. We're considering alternative protocols. So what does it look like? This is a bit of a hard question to answer because it doesn't look like anything. In this example, we've got the editor running, and you don't see Zen Server. It's an invisible background process that you wouldn't be aware of if you didn't go looking for it. However, you can open up something like Task Manager or Process Explorer and observe that, yep, zenserver.exe is in fact running. If you want to inspect its status, there is a standalone tool separate from Zen Server called Unreal Zen Dashboard that can be accessed through the editor by clicking the Derive Data button at the bottom, then launch Zen Dashboard. And its sole purpose is just to check on the status of Zen Server and provide information and stats about it. In terms of where it's running and where it's storing data, there's a lot of details to this that's important to understand. Namely, we deliberately install Zen Server to a folder under the user's app data directory. The reason we do this is that we want to ensure that you can sync your workspace even if Zen Server is running. So for that reason, we don't run it directly in place. We copy it to an installation directory and run it out of there. The other reason we do that is because by design, we're meant to have a single Zen Server instance running no matter how many installs of the engine or editor we have on the machine, even if they're different versions of the engine or editor. The intent is that the newest version of Zen Server is what gets installed and run, and it is capable of servicing all instances of the engine and editor of that version or any older version. So it's by design backwards compatible. That's where the process is installed and run from. Besides that, there's a question of where it stores its data. And by default, it also stores its data in a folder underneath the user's app data directory, a separate folder from the place where the executable resides. However, if you have set up a global local DDC path, this was a pre-existing setting in the editor, Zen Server will be launched to respect that path and store its data within that path. We highly recommend that large projects set this setting. So what should you use for the data location for Zen server? The global local DDC path should point towards a fast local drive, not a network drive, and not a cloud or virtual drive like Google Drive. Okay, so now we start talking about the roles in which we're using Zen server. The thing to be aware of is it's enabled by default in UE 5.4. It replaces the file system DDC layer on local disk. And this was an important step for us in having it in use on people's machines today before we use it for other things. And what it's given us is it allows us to avoid file system overhead as DDC file quantity gets high. In addition, it also alleviates a workload that the editor would have to worry about, which is how we do cleanup or garbage collection in local DDC. That now becomes a responsibility internal to Zen server. And another benefit we get is deduplication out of the box. Internally, Zen server is storing data in content addressable storage, which means we get the benefits of deduplication automatically. Okay, so that was Zen as local DDC. Now I'm going to talk about Zen as shared DDC. This is something that's becoming production ready in UE 5.5. This is a situation in which Zen server can replace a file share DDC on a LAN or local network. This requires manual setup if people want to make use of it. It's not automatic, the way the switch over to Zen as local DDC was automatic. And there's how-to instructions that are posted as a knowledge base article, which will be linked to later on in this presentation. Zen as shared DDC has been tested under heavy use within Epic. We've replaced one-for-one all file share DDCs with Zen shared DDCs. And that's for all of our studio locations around the world, as well as our build farm. And it's been an improvement in terms of reliability and performance over the file share DDC. It's production ready on Windows Server as a host, but I just want to be extra clear here. It's ready for Windows Server hosts, but that means Windows clients, as well as Linux clients and Mac clients can connect to it. It's just the machine that's hosting Zen server should be a Windows server. We are in the process of doing work to make it possible to host on Linux. It's not that it's not possible today, it's that we need to do the work of ensuring it's as performant and as reliable as it is on Windows Server. So one of the benefits we get from this right now is that historically, Macs attempting to use a file share DDC had to rely on the CIFS or SMB protocol implementation within Mac, and that wasn't always the most reliable thing. Now they're on an equal footing with any other client because we're using our own implementation for the client code. Okay, all right. We've covered a few things. They've addressed some aspects of our list of problems, specifically the sensitivity to DDC latency and hit rate, and the fact that we aren't using multiple cores very efficiently. All right, that's a couple things, but a lot of problems remain. So far, the things I've talked about have been pretty transparent one-for-one swaps. The stuff coming up is more disruptive. So let's have a closer look at cooked output. We are writing 1 million plus cooked output files, and this stresses the file system. What we found is on Windows, simply deleting the cooked output folder could measure as long as 20 minutes in duration when the file quantity is this high. And when we look internally at what's going on, the NTFS transaction log is filling quickly with many writes and deletes. And when full, it triggers a flush of this transaction log, and that blocks all reads and writes to that volume until the flush is complete. So one thing that we had considered is, well, okay, things like deleting the cooked output directory, we can do that asynchronously. Well, you can do that asynchronously, but when that flush happens, any read or write that is happening from any other thread is also blocked until the flush is complete. Okay, so this is a bit of a tangent, but I think it's worth people knowing about. Windows enabled last access time tracking by default in a non-server installs Windows in a Windows 10 patch in 2020. This had a number of consequences that people may not be aware of related to file system performance. The end result is that it can be punishing to editor startup and load times and asset registry scans. So, and this is very difficult to profile because of the way last access time tracking works on Windows, where it only updates if the last access time was greater than 1 hour. So run to run, it can behave very differently. So my suggestion is please consider disabling last access time tracking on your workstations. If you don't want to do it domain-wide, there is a engine plugin named Editor Sysconfig Assistant that can be enabled for your project, and it'll show up in Editor and say, hey, this system configuration setting is affecting performance for your project, and offer to change it for you. Okay, back to the topic at hand, cooked output. So fundamentally what we're seeing is that we're scaling past the use case for the file system, and the file system semantics around read and write transaction flushes, they're not what we actually need. So this is where we introduce Zen as cooked output store. So what we're doing here is we're writing cooked output to Zen server. That means the cooked output no longer shows up as files in the saved cooked platform directory. Instead, it gets stored in Zen server. There are a handful of cooked output files that we still end up writing to the file system, metadata, INIs, and a few additional files specified at cook time. They get written to the file system and then externally referenced by Zen server. So Zen server is aware of them, but it's not storing them internally. Everything else is stored in Zen server. Besides being able to write to Zen store, for our pipeline to function, we also need to be able to read back from Zen store so that staging, for example, can get the cooked output and do its job. So when staging to container files, the Unreal tooling can obtain cooked output from Zen server or loose files on the file system and stage to a few container files, pack, utalk, or ucas. We just skip the intermediate state of having 1 million+ cooked output files. So the thing to be aware of is that it is off by default. Even in 5.5, it's off by default. You have to opt into using it through project settings, where you can enable the Use Zen Server's Cooked Output Store. That's how it's labeled in 5.5. One thing to be aware of is you must also use IO store for this to be effective. This is just to limit our configuration matrix. IO store is enabled by default. That only matters to you if you've gone out of your way to disable it for some reason. So what impact does this have? So first things first, if you have third-party tooling that relies on the presence of cooked output files, then that may require a change. So that's something you need to be aware of. Besides that, in terms of debuggability, some people expect to be able to spelunk through cooked output files and as part of their debugging, and that's not possible when the data is stored in Zen server. So we're currently investigating options for exposing access to the cooked output without compromising an efficient pipeline by default. Our goal is to have Zen as cooked output store enabled by default in UE 5.6. The debug features that we have in mind is to expose a web UI that allows you to navigate the contents of Zen server, seeing which projects are stored within it, and then going into those projects, seeing which individual cooked outputs, like a Windows cook, is stored within it, and then seeing the individual items within that Windows cook, and being able to fetch those items, having them downloaded through your browser and ending up on the file system so you can inspect them as you would normally. Okay, so cooked output, Zen's cooked output store addresses this single line item of writing thousands to millions of files as part of the cook phase. Okay, not huge in and of itself. We've influenced the cook. What about other stages? This is where we start to introduce Zen streaming to target platform. This is experimental in UE 5.5. So what we're doing here is we are looking to minimize copying and transformation, shuffling around bytes into pack, UTOC, UCAS files, and compressing things. That makes sense when we're shipping, but why does it matter when we're iterating? Could we just skip it? In addition, we often don't want to stage to containers at all. So when using the editor quick launch, it builds and launches game. It stages to a non-pack target, which historically has meant just a one-for-one copy of all of the cooked output files from the saved cooked folder to the stage builds folder. How does that work when Zen server and the cooked output files weren't written, or when we're storing the cooked output in Zen server and the cooked output files weren't written to the file system? And then finally, we're using Zen over network sockets on the local machine. Could the game executable on another platform, console or mobile device, connect to it remotely? Spoiler alert, the answer is yes. So what does Zen streaming look like? Well, what it means is when we stage to container files, stage to pack files, that process takes everything out of the cooked output out of Zen server, stores it in the container files, and that allows deploy and run to happen as it did in the past. So that matches the historical patterns. When not staging to container files, we leave the data in Zen server. We don't copy it anywhere. It's just there. The staged build becomes just the executable and some config. And the game is then expected to connect to Zen server and get its data over the network instead of attempting to load it off of disk. The end result is that streaming the data from Zen server greatly reduces the duration of stage and deploy, and it opens up options for faster content iteration. What we're doing here is that we want the data to stay at rest and minimize transformations. So we want to avoid copying the data on the workstation, compressing it, copying it to the target platform. This reduces delay during content iteration and eliminates the need to restage and redeploy as you make and cook changes. All we put on the target device is the executable and a few non-streamable files. As I said, this makes staging and deployment fast. The game on the target platform gets a small file called ue.project_store that tells it identifying information about where to get the actual cooked data from, which machine it's on, port, project identifier, et cetera, et cetera. And then the game on the target is reading the data directly from where it's cooked. We don't have to restage or redeploy. When you've cooked content, it'll be read directly from its cooked destination. And then finally, the other big difference is only the data the game loads, it needs to be streamed over to the target device. This is not like where you're staging, where it's everything that was cooked for your project has to be copied over. It's only what's accessed that gets streamed. So one of the first questions we often get asked is, does this connect and stream fast enough? Like, is this viable to pull all of our game data over the network? So the thing to understand is that the data is streamed over the target platform's retail network, not a dev network, but retail network. And that means we want to make use of a wired connection, which on consoles can be 1 gigabit to 10 gigabit. And on mobile devices, we want this to happen over USB. We do not want this to happen over Wi-Fi. That's not likely to be fast enough or low latency enough for this use case. On Android, we recommend USB 3.2 Gen 2 as a cable and not using Wi-Fi to stream this data. On iOS, we're still evaluating options. The iPhone 15 Pro is the one that came with the higher speed data cable support and is preferred. But again, we're still evaluating things on iOS. At this point, I just want to stress, this is for developers who are making content changes and want to see them quickly on consoles and mobile. This is not for programmers or QA who are trying to test game streaming performance ahead of release. That will always be more appropriately done by installing the full data set over to the target device. And that workflow doesn't go away. It's just now you have a choice to either use that or stream from Zen Server. One implementation detail that's important to be aware of is that for security reasons, Zen Server doesn't accept connections from any other machine. By default, out of the box, it's limited to only accepting connections from the local host. If you want to make use of Zen streaming, then another machine, console or mobile device, needs to be able to connect to it in order to stream that data, and that requires some manual configuration changes as shown here, and that's only appropriate if you are in a trusted or LAN environment. This is not something to do on an untrusted network or public internet. And you can see there what's involved in making those configuration changes in the default engine.ini to allow a remote network service for Zen and to allow Zen to keep running even after the editor has closed by not limiting its process lifetime. Okay, so some context. You're gonna see some video here. It looks high speed. What I'm demonstrating is a replay of Fortnite Battle Royale on PS5 at an accelerated replay rate. What I mean by that is not that I've gone and sped up the video after I recorded it. Rather, I did a gameplay replay on the PS5 at an accelerated rate, meaning it ran at this speed on the PS5 originally. My point in doing that was that it demonstrates that even with the additional stress of accelerated playback, we're able to stream data successfully over a network link to have a good in-game experience. The table on the left shows the difference that this workflow has made. So a staged build that is staging to containers produces an 89 gigabyte directory footprint, whereas staging to Zen streaming is only 4.6 gigabytes. This dramatically reduces the time it takes to stage. Again, 18 minutes is shown there, 18 plus minutes is shown there. The time it takes to deploy, nearly 7-minute reduction. However, boot and load takes longer. Fundamentally, that comes down to the fact that streaming from Zen Server is not as fast as reading from local disk. That is a reality. However, that increase in boot and load time is more than offset by the time savings of stage and deploy. So the net result for a person trying to iterate is 25-minute reduction in duration. This is the same example, except from Android using the Lego Fortnite game mode. And again, we see similar behavior where a container build was 30 gigs. However, with Zen streaming, it's only 15 megabytes. There's platform-specific differences about whether the executable ends up in the stage directory or not. So there's a whole bunch of details as to why it ends up exactly that value. But the result is always that you're staging to a much smaller output. And this reduces the time it takes to stage, the time it takes to deploy, but you do pay a penalty in boot and load time, and it's important to be aware of that. However, it's the net result is still 9+ minutes of time savings. We are actively engaging in efforts to see what we can do to reduce the boot and load time impact by doing things like caching on target platform, as well as looking for bottlenecks in our the loading code that makes use of Zen streaming. However, to a user, this is faster turnaround time, and the in-game experience is indistinguishable from if they had it installed on their local device. I should mention as well, I've put these graphs on this screen. They illustrate the throughput in bytes as well as the number of requests happening to Zen server second by second. Okay, so choosing to make use of Zen streaming on target platform has addressed a whole bunch of our challenges in the stage and deploy phases of our pipeline. So that's great. I think at this point it's good to just stop and think back to where we started and where we're at. This was the diagram, the illustration of where we started. Again, make note of your stage build was 65 gigs spread over 80 files, and that same build had to be deployed over to the target device. Now, when we're using Zen streaming and the aforementioned features, our DDC data is in Zen server. Our cooked output data is in Zen server. It's high granularity. It's still 1 million items. However, that's not 1 million files on the file system because Zen server is choosing how that's represented, and it's much more aggregated. And crucially, because we're streaming, the size of our staged game has gone down to only 5 gigabytes over 50 files, and that's all that needs to be deployed to the target platform. And then once you launch your game, it is able to connect to Zen server and stream the data that it needs from there. Okay, so stage and deploy are in good shape, but we want to do more to reduce the cook phase. This is where we start to introduce a couple more features. Specifically, we'll start with Zen snapshots. This is something that's experimental in UE 5.5, and the premise behind this is that we don't want to cook when we don't need to. So if a cook has been produced elsewhere by another person or on the build farm, you should be able to get it efficiently. And getting a cook should be equivalent to cooking for yourself. So there are existing mechanisms for getting staged container builds or fully project game images, but that's not the same as you having cooked the data yourself. They represent later or different states in the data pipeline. So what is the equivalent of what we could do in the past? That is copying a cooked output folder. What's the equivalent of that when we're storing our data in Zen? Well, when Zen server holds the cooked output state, can we relocate that from one machine to another? And is there anything outside of Zen server that's an expected part of the cooked data? So this is where snapshots come in. They represent the ability to export and import cooked output state for one or more platforms from Zen server and store them in either Unreal Cloud DDC server, another Zen server instance, or as a file archive. This is done efficiently by getting and transferring only a delta of what doesn't already exist in the destination. So we're still building up the tooling around this, but in 5.5, you do have access to a UAT task called Zen Export Snapshot, and the build and test project XML build graph that ships with the engine demonstrates the use of Zen Export Snapshot and provides an example of how to export snapshots to Unreal Cloud DDC from your own build jobs. One thing to be aware of, exporting a snapshot writes a small snapshot descriptor file, and that file is just a few lines of JSON that describe where the snapshot data is stored. And this becomes important when you're now trying to import a snapshot. As before, we're still building up this tooling, but in 5.5, we provided access to a ushell command, .zen import snapshot. You can pass as an argument to that the snapshot descriptor path, and it will import the described snapshot into your local Zen server. And at that point, you are in the equivalent state as the machine that did the cook that snapshot was exported from in the first place. It's also important to be aware that snapshot data stored in Unreal Cloud DDC can be replicated between regions. So what this can look like is you might have a build farm in a particular regional location. So let's say your build farm is in US East, hosted in US East. And you have builds that are publishing snapshots at some cadence. from the build farm, and they publish to the US East Unreal Cloud DDC server. A user in another regional location can be talking to the Unreal Cloud DDC server in their region. In this example, a user in Europe could be talking to the Europe Unreal Cloud DDC server, request that snapshot. Behind the scenes, the Europe Unreal Cloud DDC server is fetching whatever it doesn't already have from the US East server and sending the result back to the user who requested it. This data is replicated and cached so that the next user who asks for it will find that everything is served to them immediately from the Europe server without having to go fetch anything from the US East server. And all of this is done in an incremental manner, so only the difference of what they don't already have has to be downloaded. Conceptually, snapshots encompass the entirety of the cooked output for a target platform. They don't contain the executables for that target platform, so you need to build or get those separately. And once you have imported a snapshot, you are able to do everything you could do if you had cooked that data yourself, meaning you can stage to a Zen streaming build, then deploy and run that. You can stage to a container build, pack files, deploy and run that. And crucially, you should be able to cook incrementally on top of it. And this leads to the last subject that I wanted to discuss, which is incremental cook. This is a future work item that we're working towards for UE 5.6 and beyond. And fundamentally, what this is about is we only want to cook what needs to be cooked. This has been a long time goal. Iterative cook has existed for a long time, but it didn't recognize all types of dependencies that exist within our data. What we want to get to, our target workflow, is you get a base cook and build only your changes on top of it. For us, that's the optimal arrangement and brings duration of target iteration into the range that's acceptable for more people. And the way we're approaching this work is we're trying to take a reliability-first approach. And that means excluding types that we know have dependency tracking issues, even if it means assets containing those types have to cook fully each time. That's how we're breaking down this problem into pieces. So, one of the important questions we had to ask ourselves as we started to go about this work is, how do we know that incremental cook is producing correct results? Are we just hoping and then we'll wait for somebody to report an issue to us? That's not really what we were after. So what we're doing is we've got automated jobs that cook incrementally at head revision of our internal projects, Fortnite and others, and compare the output with that of a full cook. This is a byte-for-byte comparison. And when there are differences, they can be due to non-determinism, or they could be due to a gap in dependency coverage of our incremental cook. And we've been using that to get a better understanding of where those gaps are and following up on them and getting them addressed. So our goal is to be confident that it's suitable for developer iteration. I want to be clear that it is separate to get to a point where it's suitable for shipping builds. That's not what we want to use incremental cook for at this point. What we want is for it to be suitable for developer iteration. Internally, there's a lot going on to track dependencies to try and make this reliable. Sometimes people think, oh, well, packages declare their imports. Those are the dependencies, right? No, not exactly. There's many more types of dependencies, and even the imports aren't necessarily all cook dependencies. So for example, you can have dependencies on non-asset files. For example, a shader, USF or USH file. You can have assets on another package. You can have dependencies on a CVAR value. You can have dependencies on an INI config, as well as class schema, meaning the description of the fields in your types. If those change, the cooked data needs to know that it needs to rebuild. So that has to be represented as a dependency. And really what we're after is addressing these last 3 big issues with the cook phase through the use of incremental cook. There'll be more to come on this subject in the future. Okay, wrapping up. We set out to do improve content iteration speed on consoles and mobile, enable content iteration on target platforms, be closer in speed to code iteration on target platforms. I'm not here to say mission accomplished. However, we've set out a path that allows us to get to that destination, and we're continuing to work through that path. The thing to be aware of is there's a number of separate distinct things that are helping with this, each of them completing on a different timeline, whether it's stuff that was production ready in 5.4, stuff that is production ready in 5.5, beta in 5.5, or the items that are experimental and are going to be completing in the future. So I promised documentation. The situation I want to avoid is one where people hear about this stuff but then get back to their desk and don't know how to make use of this stuff. So for that reason, I've put up some documents that are step-by-step how-to documents for how to set up Zen as a shared DDC, how to use it as cooked output store, how to make use of Zen streaming, and how to make use of cooked data snapshots. And that's it. So if anybody has questions, please feel free to come up to the mic. I think we've got 5 minutes for questions.
yellow. Hello, everyone. Welcome to 10 tips for making real-time apps in Unreal Engine 5. My name is Matt Workman, and I'm a solo developer based out of Boston, and I make apps / games / sims for the film industry. And if you take nothing away from this other than this next bit, that if you have an idea for an app, as simple as it is, whatever industry you're coming from, I came from the film industry, didn't really have a software, and definitely didn't have a gaming development background. Came from the film industry, had an idea to make lots of little 3D cranes, and I've been kind of chasing that vision for a couple of years here, and it's been successful for me. And if you have an idea like anything like that, Unreal Engine's a great place to start building that into possibly a business and a career. So to get started, I just want to get through some quick tips, like getting started in the engine, quality of life stuff that's caused me headaches and hopefully save someone just a little bit of time in the future. When you first get into Unreal Engine, you're going to grab the latest version off the launcher here, but over time you will become a hoarder like me. You will just accumulate these engine installs. They're very big. And the same thing will go from anything from Bridge, the marketplace. Just in the beginning, try to get that stuff off of your main hard drive, put it somewhere else. Plan for growth. I have every version since 4.18. It's a lot of space. We want to get that somewhere else. Next, for marketplace, any assets you're bringing in, I would really recommend building what I call burner projects. It's just a big folder. I'm going to put everything in there, and I'm going to bring every marketplace asset. Anything I'm testing is going to go to a different project, and I'm going to really look through it, look at its structure. And the main reason for this is that once you have assets in your project, moving them, renaming them, deleting them, like I'm just going to rename a folder, it's a little bit sticky. Everything's kind of codependent. So you want to be really careful what you bring into your main project. And so I just have this folder of all this stuff. I'm just testing, and then I can just go in there and just delete it when I need space back. And the core thing that you want to be checking for is that you're going to migrate only what you need precisely to your main project. You get to look at the dependencies, and your project will get really cluttered if you start bringing in the demo maps and game instances and all this kind of infrastructure that usually comes with it. You really don't want that in your main project, so migrate it in. It takes a little bit of time, but it's really worth it in the beginning. My last little getting started tip here is to create a blank map. Easiest thing you'll ever do in Unreal Engine, just literally nothing is in this map. And go to project settings, make that your editor startup map so that when you start up the engine, nothing's loading, you're not wasting time. And if you end up corrupting a map that you're working on and it's your startup, you can kind of get in this kind of infinite loop of never being able to open the editor. So next I want to get into the Unreal Engine 5 features that I'm using, the things that make this Unreal Engine 5. Why did I move to Unreal Engine 5 from 4? And to illustrate this, I'm going to be talking about one of the apps I make called Cinetracer 2. I have another version in 4.27, but when early release 5 came out, I was like, wow, all these lighting features. Let's see how this goes. It's been a mixed bag journey to get it into UE5, but I'm pretty happy with where it's at right now. So Cinetracer 2 is a lighting visualization app. So this is for filmmakers to put some lights up and see what they look like, right? Unreal Engine's a great place for this. And so the things we're leaning into for this are Lumen Global Illumination, Lumen Reflections, Virtual Shadow Maps, and I don't think we call it Lumen Ambient Occlusion officially, but that is a huge component of making the lighting look realistic. So Lumen Global Illumination is bounce lighting, really important. Next, reflections is for mostly shiny chrome objects. We're going to get reflections, not quite RTX, like you can look in the mirror. It's not quite like that, but it's still very nice. And Virtual Shadow Maps is going to give us what was previously something like RTX shadows. If you have a larger light source casting a shadow, it's going to be softer. So all those things put together is going to make a sort of realistic lighting simulation. Unreal Engine is really good for that. And the ambient occlusion, I'm going to try to pick out a little clip here, is going to make contact shadows. If you have, say, the skylight overhead and you put a ground over it or a ceiling, there will be darkness under it. And this sort of comes all together. So this is a little clip of Cinetracer 2. It looks very much like an editor mode. In the beginning, it was sort of supposed to be kind of a Fortnite creative hybrid, but really it's kind of turned into this, almost looks like Unreal Engine and Sequencer, and some people sort of mistake it for that. But this is just a look at some of the UIs and programming a little bit of a camera move here and visualizing it. But to really appreciate the lighting of UE5, I have a couple clips. This is an interior in Cinetracer, entirely dynamically lit by the lights in these scenes here. It's not much compared to the Mega Lights demo that just happened, but the overhead linear lights, they can be dimmed, you can change the color. All of this is fully dynamic and cross-platform as well. So that is a change from RTX before. This is NVIDIA, AMD, and macOS, which you'll see is going to be a big component of the stuff that I do. This is another scene that I've created for Cinetracer 2 after like a pretty famous lighting setup. And other than the really like over-the-top caustics, which is like the cool call-out, if you look under the tables, you would see it kind of fade in, and you look at the bounce lighting coming up. The bounce lighting from the floor and the darkness under the tables, that's what makes this feel real. This is a recreation of a famous stage in LA. I think it was called Popsicle at one point. I think they rebranded, but you've certainly seen it in magazines and movies. Fun one to recreate. And to really show off lumen here, it is lumen emissive. Is this entire ceiling, it's just a plane. You make it shiny, or I'm sorry, emissive in the material, and lumen does the rest. And I've been digging into megalights quite a bit, as one you'd assume, because I'll be likely testing that here. Megalights, I believe, doesn't do the emissive side of things. So you would still be doing emissive this way, and megalights is really, from what I understand so far, point lights, spotlights, and rec lights, surprisingly. That was actually supposed to come out, I believe, in 5.4 when it was called many lights, but we digress. So that's lumen, makes a great lighting visualization. So if anything you're making needs to have realistic lighting, this is a great tool for that. However, lumen comes at a cost, quite a bit of overhead. To get to, say, 60 frames per second, you're going to need to be on a high-end gaming laptop. For PC and on the Mac, you're looking at like minimum like M1, M2 Pros maxes to be 60 frames per second even, right? So lighting, if you're coming from visualization, understandably has a cost. So another project I'm working on is called CamOp Simulator and CamOp. No one will confuse that. It's perfect branding. It's never going to get confused by anybody. But this is a camera operating simulator, and people have described it as AIM Labs for videographers. So you'd have to know gaming and videography for that to hit. But the point being is that the frames per second here, the frame rate, the performance is actually the first most important thing. So in the year, what year is it? We'll just say I only know it by Unreal Engine versions. This is 5.4. I treat this like it's Unreal Engine 4.27 because frame rate is crucial, and you'll see that I'm actually building this for mobile as well. I do not use Lumen GI, don't use reflections, don't use virtual shadow maps. I am in like what feels like the Stone Age of Unreal Engine, having worked in using Lumen for the last couple of years, but then frame rate is super important. So you can turn it off when frame rate is really important, and for mobile, it's also a good idea probably. So I'm roughly targeting 90 frames per second. Really, it's actually much higher, like 120. And we're looking at M1 Pros, and Maxes, of course, are gonna do even better. And on like 2080, 2070, and above, again, 90, really in the hundreds of frames per second. We really need this, as you'll see, for some of these simulations for it to feel good. iOS, a little bit different. I'm currently frame locking for iPad. You can also do 60, but for battery reasons and other things, you may not want to like crank 60 frames per second on someone's phone or iPad. So there's a lot going on here, many views and whatnot, but what you're seeing is a drone, and on it is a gimbal, which is a machine that's going to pan and tilt the camera. And one way that these are controlled are with these two wheels at the bottom. One's panning, which is a yaw, and the other one is tilting, pitch, I believe. And people do this in real life. This is something that someone has to do. And someone is piloting the drone, someone is operating the head. The head is sometimes done with a joystick, but it is also commonly done with wheels. So these are fairly high stakes operations, as you would imagine, and I make a simulator that does just this, that they can practice. And frame rate is very important for this. So just wanted to recap that for Unreal Engine 5, we can lean heavy on the lighting. I'm jumping right into 5.5 and doing some megalight stuff, there's no question. But if your project doesn't require like the most accurate lighting in the world, and performance is like really important, you can just turn it off. It's in project settings right here, big ol' list. So one of my projects, it's all on. The other project, they're literally all off. And I developed them at the same time. Alternatively, if you want to have a section of your map, as it were, having realistic lighting, having bounce lighting, and these reflections, you can designate this with a post-process volume, which is literally a box. So it's like in the box, realistic lighting, outside of the box, UE4-ish kind of lighting. And one example I saw online, not from mine, but it was some game that like it was open world, and the exteriors with all the trees and whatnot didn't need lumen. They kept that off. But as you transitioned inside to like a tunnel environment, there's like lanterns and it's megalights, and you can kind of visualize that. They had a post-process volume around just the interiors. They used lumen. So you can do this hybrid approach, and I'm sure there's even more clever things than that. But those are the kind of ways that I look at it, either completely on or off, or make a little box, a lumen box. So moving on, I'm going to be talking about macOS and iOS, because for the film industry and a lot of industries, I imagine, Mac is actually really, really popular. But if you were to talk to like most indie game devs or game developers in general, a lot of them are just like, I don't even mess with that. But as you're building for apps, and especially like iOS apps, it's a really big deal. You know, macOS, you know, the MacBook Pros, the iPad Pros, they're just really convenient. They work. You know, if you're using an iPhone, it's the whole ecosystem, right? So what kind of goes into making apps for Mac OS and iOS? And I just went to all of the Mac OS and iOS stuff presentations yesterday. So what I'm saying, I double-checked it. This is fairly up to date. So this is CamOp Simulator. I released it last month. It's actually been really successful with camera operators. You're going to see this on set a lot. And when I show the mobile version, you can see it, I think, like everywhere. But as we look at it, these are cherry-picked. This is just a sea of Apple computers. As I was starting to put this app together from concept and like asking people, like, you know, like, what do you want and like what kind of computer are you running, the most common spec was an M1 MacBook Pro, right? So M1. I don't know when that came out. It's not, you know, it's not a high-end gaming computer, right? So this is like my target spec when I'm going for this app. So for macOS, if you're getting started into it, as of 5.2, I believe, they added Apple Silicon native support. So there was this like really awkward transition between Intel and Apple Silicon, and the engine took a little time to catch up. But now as of 5.2, that's when I started making Cinetracer 2. We have full Apple Silicon support for native. Performance is certainly better. And we actually can still have Lumen GI, Lumen Reflections, and virtual shadow maps. So realistic lighting is very possible. But again, to have like kind of, you know, pleasant frame rates, you do really need the Pro and the Max. And the Max is really the best to get those frame rates there. Below that, it's certainly not uncommon to be at 15 frames per second or something like that with like an entire interior with as many lights as I've shown. As of now, there's no Nanite, or it's in beta. I think in 5.5, I saw a graph, but I was like sitting kind of bad. I was sitting in like that seat, and I couldn't take a screenshot of it. But it's coming, and I haven't heard anything about Grooms, but they're working on feature parity with Mac OS. Probably not for iOS, but certainly for the desktop, or maybe it's coming. So to do this, it does require a Mac computer. This is a common question I get a lot by people who are trying to make stuff for it. You do need some sort of Apple hardware to do this because it requires Xcode. But if you look at this screenshot here, that is my main Apple workstation. It's an M2 Mini 8 GB. So very simple, very humble. I usually try to get the most affordable like Mac of the time that I can get. And I build both Cinetracer 2, Heavy on Lights, and CamOp iOS and CamOp Simulator, Mac OS, from like pretty much the minimum SKU Mac you can get. It goes fine. It's not fast, but it gets it done. It also requires an Apple developer account, which is a bit of friction, costs money, it just takes time. It's like $100 a year-ish, but it will allow you to develop and publish apps for Mac OS and iOS. So it's you know, if you're going for multi-platform, it's pretty worth it. And the most painful part, which I just got confirmed from the Apple talk that they had yesterday, that to publish to Steam, I'd assume for Epic Games Store, certainly for the App Store, the Apple one, for macOS, you have to manually code sign and notarize. There's a new workflow I'm going to show about where it kind of automatically does it, but as of yesterday, they told me that notarizing is not automatic, so you're going to have to look into that process. That is the worst process. That took me like many months to get that streamlined. You're in the terminal, it's bash commands, it's like very stuff I don't typically want to be getting into, but that's the hardest part for macOS. For iOS, good news, 5.3 introduced the modernized Xcode workflow, code signing. Now I'm questioning if notarizing is actually automated. I think it's not. I'll have to look at that. But this is getting more streamlined. Yesterday they were talking about it. They're trying to do this, the packaging of the apps, more the iOS way, the Apple way, the Xcode way. So it's getting easier and easier. And I've just started very recently building for iOS and test flighting, which is kind of like Apple's beta. And it's actually really streamlined compared to what I have to do for macOS. So it's certainly getting better and better. Requires the same Apple developer account. I use the same one. And publishing to Xcode, which you have to basically use Xcode these days, it's actually getting really easy. And my workflow is that you basically package the game, then you open up this iOS project, and you hit archive. This is the latest workflow. And then you just upload it right to the Apple Connect store. And then I can just remotely download it on test flight to my, this is a lav, but usually my phone, to my iPhone, to my iPad, and to all my platforms. And if I had an Apple Vision Pro and you do it right for the iPad, it just natively is a window on Apple Vision Pro. So that's how Apple's kind of made this like transition to what do they call it? What's their branding? Anyway, not an AVP talk, but you're publishing for all at once. It's really streamlined to get it onto all the different hardware. You don't have to plug it all in, so it's really great in remote. So this is a world premiere here. I haven't shown this online yet. It's really hard for me not to post every day about this, and I've had this for a while. So this is CamOp, and this is the iOS version of it on an iPad Pro Gen 3, which is relatively old, but we have a full walking MetaHuman. I was impressed. I haven't been putting MetaHumans on iOS before. And there's a render target. We do cap this at 30 frames per second, and we have touch controls as you would want for a mobile-first app. But you can also control it from these wheels that plug in. And this was a fun pickup. I was originally not going to build for the phone, but I was like, let's give it a test. And I think this is like a 12 Pro or something like that. It's cooking. This is a MetaHuman walking. We have a camera whipping around, and pretty excited. I think most of the kind of mechanics I usually write, we're switching views, we're zooming in over here. Now that I have this workflow down, it's pretty fluid to design for PC, Mac OS, iOS, iPad OS. They're kind of the same thing, or they're very similar. And even the iPhone, though you have the little cursor. I don't know how to get rid of the cursor right now. Again, this is all working through across all these platforms. And this is not because I want to develop for Mac OS and that it's pleasant and fun. It's just that this is where the users are. And I would definitely guess that if you're building apps and you want to reach as many people as possible, that this is a good platform for you to kind of look at. So next, I want to talk about enhanced input. This took me a little while to get through, so I hope this helps some other people looking at it. If you came from Unreal Engine 4, I forget when they introduced this, but I didn't switch to using it until Unreal Engine 5, when the big yellow text got added, the D word, the deprecated word, this old way of going into project settings and just listing all your inputs. That's how I learned. That's, you just go in there, W is forward, S is back. Big list, it's always on, was a concept that we didn't have to really think about back then. That is gone. We don't really do it that way anymore. So it took me a little bit once I switched to 5.2 to get into this. So before, just a big list, all the inputs. Now those inputs are basically all little assets called input actions. You right-click, you make them here. I don't know if you can do it in C. I bet you probably could. And you're also going to make your input mapping context here as well. So these are all the inputs. Actually, this is about a third of the inputs for CamOp Simulator, which has kind of like an insane input system. So it's not your average way of doing it. But you're going to have all these input assets in a folder. That's very different from before. And you're primarily going to say, is it a digital Boolean, which is like a button press mostly, 1D axis, 2D axis. That's all it. That's it. You're not even saying what button it does yet. Next, you're going to make an input mapping context, kind of a big word, just a big list of all those. And what was previously in project settings, you would make more of those. Like before we had one huge list, now we're sort of inclined to make a bunch of smaller lists, smaller input mapping contexts. And here, looks like you would want, you're going to say that that input action that you named, in this case I have an example called drone turn, same as any pawn, right? A and D, it's gamepad, that normal mapping. But you're breaking them into different lists. Why are they in different lists? This took me a long time to figure out, to do right. After that, it's much of the same. Your player controller or your pawn can then implement the input action. So this is normal. It's OK, this is probably a digital Boolean, started, triggered. It's questionable, depends what you want to get done. But what does it do when you hit the pause button? You're going to implement it, likely player controller or pawn. But if you stopped right here, unlike Unreal Engine 4, you made the input actions, you made the IMC, you implemented it, and you hit play or run, nothing's happening. No input will ever make it to the game. Different for enhanced input is you need to go to player controller, you grab this subsystem for enhanced input local player, and you're going to add that mapping context. You actually have to activate and add those inputs in. We didn't do that in Unreal Engine 4, or pre-enhanced input. The new thing about this here, the new paradigm, is that you can remove the mapping context. So why would you ever remove inputs? In 4, we never. I never designed entire systems and never did it. It wasn't possible, perhaps. So I have just a little example of how I've come to understand it. There's layering and priorities, but this is a simple version of it. And I tried to make anything in Unreal Engine as simple as possible for myself. So we have a player controller, and you might then go to the player controller and add your default IMC. And these are things that are going to be always on, like your pause button. Things that aren't going to be changing their functionality pretty much ever, right? And there's usually not many of those. So next in execution, we're going to possess a pawn. It's like a helicopter. Here's a drone. So we're going to possess this pawn. And then Epic has this set up for their vehicle template, and I've started to adopt this, is that the pawn itself is going to store a reference to its controls, right? So its throttle, its turn, things that are only domain specific to that pawn. it'll link to that IMC, and it's going to load those in. So both of these orange rounded boxes here are IMCs, and they're lists of inputs, and they're both added to the master list. They're both on at the same time. As we switch to a different pawn, I want to possess a vehicle pawn. We're going to possess the vehicle pawn, and then that pawn is going to then reference, like, these are my inputs, right? So now it's steering, now its throttle is driving. It's like a little bit different. And these are all on at this point, and you're going to have conflicts very likely in input, like your WS, your whatever inputs, they're going to conflict. So you don't want them all on at the same time. So what you would do is you would just simply remove the entire IMC from the other drone. And so it's pretty basic when it is laid out like this, and then you might have, if you're not using common UI and you put up a pause menu, W and S before were like moving around, now they're navigating menu, you would just remove the IMCs, add them. That's just not a concept I was using in UE4, and it took me an entire project to get a good version of that working for my current game. So next I'm going to look at some UE plugins here. So as you're getting started in building mechanics, and it's something completely original, you really should be searching the internet, the entire dev forum, whatever you feel like that you can find this information. See if this mechanic exists in Unreal Engine already. It's very likely that something very close to it exists already, and you want to find that template, that one node. If it's buried in C, unfortunate, you can go get it and expose it to blueprints if that's how you're programming. But very, very likely the framework exists already, and you should start building at it, using it for like your prototyping. So for an example, for my CAM-op project, I needed what's called a pursuit vehicle. So it's a car chasing another car in pursuit to film it. And rather than starting from scratch, I just went to the vehicle template and just grabbed the off-road vehicle. I just slammed another skeletal mesh on top of it. That's my crane. And then on top of that, at the end of it, a gimbal, right? And just kind of Frankenstein this rig together. It's relying on vehicle movement component, right? Built into Unreal Engine, it can drive. But there's lots and lots of built-in components that you can go surface that are not as well known. So the first version of this, we have literally the two template vehicles chasing each other, and the gimbal has a little bit of physics, and the arm can move, and I'm live controlling the head. So this is enough to get the prototype out, enough to put online, to get feedback early on. And this launched with the first version. It was pretty good, but we had some kind of like feedback and improvements to make. This was like 2 weeks ago. So from that, starting from the base, just like kit bash this thing together with existing assets, we went back and basically built a wheeled vehicle from scratch. So in this case, I have a lot of modeling to finish on the Porsche Cayenne here, but modeled out roughly a Porsche Cayenne. And as the exact same mesh, it's all one mesh. We put the arm and the gimbal at the end. It's all one mesh, doing the wheeled vehicle set up correctly. And then a lot of control rigging. This is actually the cinematic control rig for keyframing it, and the runtime one's even bigger. I'm not able to even show it. But point being, start with like a template, get something rough out there, especially if you are into like showing people what it looks like early, get the feedback, get it like overall running, and then come back and kind of refine and build it out. So the thing to look at with this one is specifically, as a car is going to like accelerate, the gimbal's going to do this. If it's going to go backwards, it's going to go forward. If the car turns like this, the gimbal goes like this. If you've ever seen behind the scenes of this gimbal at the end's whipping around. And so how do we get the physics of that? You actually have to make it all one skeletal mesh for the physics to work as a vehicle and that happening. So if you watch the gimbal as the car accelerates, it's doing the correct kind of like inertial accelerations from rotation and whatnot. And on top of that, before the arm didn't have collision and wouldn't affect the driving of the vehicle. Now it does. You slam it into a wall. I mean, in real life, let's hopefully never figure out what happens when that happens, but this one kind of like reacts and will actually affect the center of gravity of the vehicle. And we tune this to be like halfway between arcade and somewhat realistic, right? So this would have taken me, in my opinion, I launch fast, but this would have taken me too long. If I had taken the 2 weeks to build this originally, that's a little too slow. I like to prototype really quickly, but then after refine and refine. So like, get existing assets, prototype it, get it out there, even have people beta testing it before you get to the final one. That's my approach to it anyway. Another example here, I needed to build a drone, which I hadn't planned on doing, but the aerial cinematography community found me and were like, please do this. And I was like, that sounds like fun. And so the way I made this drone fly is very similar. I 3D modeled this from scratch. It's built off of like an industry standard one, stuck a gimbal on it. And this is just your regular old pawn. This is just a character movement component. You can set it to flying, so it'll kind of just hover. It doesn't really like gravity and like kind of fall down like really. The wheeled vehicle can kind of do that, but it's literally just the existing pawn. Not the most realistic physics. So after that, the FPV drone community found this project and asked for an FPV drone, which the difference is like kind of like your regular drone will just kind of stay level and hover, and it's designed for like easy flight control. FPV drones are completely manually flown, so you literally have to tilt it forward, give it throttle, and the hardest thing to do on that type of drone is to just hover like this. It's full manual, but this is where the industry has moved for flight. And then I tried to take the wheeled vehicle component, and you can use thrust. You can have a thruster straight down, then tilt forward and thrust. And it was very difficult. I couldn't really get it to fly even like remotely correctly. But luckily, this came out, I think like even, it says it, March 22nd, fairly recently. Some other developer put their entire FPV drone simulation framework on the marketplace. It's really affordable. They have an amazing Discord, so shout out Helios, save my butt. And I just use a marketplace asset as a starting place for like a pretty core system here. But this is what that pawn looks like. It's a little bit more involved, but this is a rather accurate simulation here. So we're going to care about the total mass in grams. We have max torque per propeller set here, and max thrust, I believe. They wrote it. I just built it. So a 3D model did. I made this all to scale with what's called like a Cinelifter, and then I put my gimbal on top of it. So building on top of other people's work to make something that really hasn't existed before. So this is just some early footage of it flying here. It's a rather wild system. I've been told that that's the tiny bit unrealistic how the gimbal is reacting to it. But these fly like this, and they do absolutely ridiculous things. And again, another high pressure situation where when you're learning in the field, any crash is extremely expensive. So this community really wanted this for a training simulator, and it's usually operated by two people. One person in like some like cyberpunk looking glasses, like driving the drone, another person on wheels or a joystick. So it's a dual system. So this is kind of the scope of what I'm building for that simulator. And these are really niche markets, but I think that that's actually really great these days, is to build like a specific product that solves one issue for a certain group of people. I think that Unreal Engine's really good at getting really fast prototypes for that. And that's what I've been doing for the last basically 8 years. Next is MetaHumans, just some like random tips about MetaHumans. I've been working with these since the alpha. I've been making clothes for them. They're on the marketplace. And then SoonFab. And this clip is going to have a little bit of audio. And it's just some of like the motion capture stuff that I'm planning on adding to basically all of my apps and some of that's already in there.
Hello and welcome to Cam Op Simulator. My name is Matt Workman, and in this app we're going to be able to train and practice camera operating virtually. Let's get started by learning how to pan and tilt the camera. Hello and welcome to Cam Op Simulator. My name is Matt Workman, and in this app we're going to be able to train and practice camera operating virtually. Let's get started by learning how to pan and tilt the camera.
So I've been, I'm concentrating a lot on like the cranes and the mechanical stuff, but so much of like the simulators and being on set, and how I would like it is that as you like look around, that the other people that are supporting what you're doing are going to be there. At least that's the plan. iOS, it's a little spicy to have maybe 4 metahumans just chilling in the background and pulling focus and stuff like that. But it's the vision I've been working towards since I started building this. And Epic has really provided the building blocks to get this done. Metahumans, I saw it immediately as like a huge component of what I'm building. I can imagine that for any industry that you're building an app for, having a human in it is likely. So I spent a lot of time in MetaHuman world. So here's a couple of tips with these. So when you first go on the web app and you create a MetaHuman, that name's really important. You probably just give it like whatever frivolous name you want. It's actually extremely important. And these are managed, which I didn't quite grasp that in the beginning. So you make a MetaHuman, you give it a name, and you're going to pull it down through Bridge into your project. You make another project. If you pull that same MetaHuman down, these are the same MetaHuman. If you go back to the web app and change that MetaHuman, and you go back to your other apps, it's going to try to push those changes back down to those projects. It's managed. They're not just like you download it and they're kind of just like offline assets. This whole thing is being managed from like, I think of like Epic's MetaHuman, like Perforce Cloud or something like that. And this becomes even more important as you upgrade engine versions. The MetaHumans keep updating. And at first, that's sort of like a stressful thing. And in the beginning, I was like, let's just never update the metahumans, like problem solved, right? But they eventually got toes. I was around when metahumans didn't have toes. They get new net correctives. Things happen. Metahuman animator comes out. It's like you need to update to have these features. And it's usually worth it. Luckily, this process is fully managed. As you update your metahuman to the newest one, it will push those down to the project. It gets really specific. It's like you have a 5.1 metahuman and a 5.3 project. It handholds you through the whole process. And there's a dialogue that's like, we're going to update these things for you. Do you want to do it or not? So that relieved a lot of stress for me as I went from early release metahumans to 5.2 to 5.4 was a big jump, but it is fully managed. So it's a complicated system, but they're managing it. So if it screws up, it's their fault. It's not your fault. It's completely their fault. So a specific thing that happened is I upgraded from 5.2 to 5.4, and I kept seeing it online that like, why don't grooms work in 5.4? And so this is primarily happening on Mac OS. So if you don't endeavor into Mac OS, you're going to have a much easier time than I have. But the main fix for this, you just have hair just shooting out everywhere. Anything that's a groom just absolutely explodes. Still today, because I think it's, well, we'll see when 5.5 happens, how it's going. But the fix for this, someone linked this to me on LinkedIn, because I just perpetually complain online. Someone linked me the answer. It's loveliest. So it's validating my online complaining constantly. You just go to the groom asset, and you have to turn off RBF interpolation. It's always just this one checkbox. You turn it off. It undoes whatever happened in the 5.4 MetaHuman 3 version, whatever we're on now. Absolutely fixes it. It does take a long time. You don't want to batch this process. It's like one of these takes like a minute sometimes. And I have a very fast computer. My main computer is a HPZ PC. So that's a huge fix. And the early versions of Cinetracer that were in 5.4, if you were on Mac OS, they didn't have hair. So apologies, but we got it fixed. The next thing I see that's pretty common, I've been doing a lot of sequence work and animation work to get these, simulator buddies into the apps I'm making here, is that the head disconnects from the metahuman. It's a common thing that happens quite a bit. So I want to kind of explain what I think is happening. There's a lot with metahumans you could screw up, but this is what I think is mostly going on. So you have a metahuman, and you have a head and a body. These are separate skeletal meshes. If you select the body, switch it to animation mode, and you reference an animation, everything's fine, right? Good to go. If you do this exact same thing, you grab the face, animation asset, play a face animation, not good. The head will disconnect. You've done the same thing to the body and the head. This is what a lot of people do. What's going on? And I've seen many ways of people trying to fix this, like what happened? So the way to do this properly, there's a lot of ways, but this is the default way of doing it, is that the face skeletal mesh needs to stay in animation blueprint mode, and you need to reference the stock face animation blueprint. This is what it's going to come stock from Epic Games. But you're like, how do I play an animation on this thing? Like, what's going on? So if you go into that stock included animation blueprint, you're going to have this node here called copy pose from mesh. And this is set up so that whatever mesh this skeletal mesh is attached to, so in this case, the face is attached to the body, it's going to copy the pose from the body to the face, thus connecting the head to the body. If any mechanic you do disables that node, the head will disconnect. This is the core node that you need to have in that situation. The next one, for the default setup, is a slot. That is where animations at runtime are going to play montages, and by default in Sequencer, we'll play those animations there. So those are sort of an unknown if you've never dug into that. It's really important. There's many ways to do this, but that's the default one. So then at runtime for apps, not Sequencer so much, you would then, one mechanic to play an animation on that is to not reference that animation again that disconnects the head. You would play a montage on it. And the montages play in the default slot there. Another way of doing this is if you take that copy pose from mesh and you put that in the pose process blueprint of the face, that also can work. Then you could reference it. And it just gets more and more complicated from there. But that is the core reason that the head would separate. And that's at runtime. Sequencer is in a completely different machine. Animating a metahuman in Maya with a control rig is completely different than editing a metahuman and animating a metahuman in Sequencer. In Unreal Engine, there is so much logic firing. You can kind of zoom out and think that it's just moving and animating, but there is so much logic firing in this blueprint, so it's a little bit more nuanced here. I'm going to go back. So again, with the body, similar to populating it, going to animation asset, putting an animation in Sequencer, you do the same thing, works great. I should have made a visual for it, but what it's going to say is custom mode, which is sort of leaving letting sequencer kind of drive it. Again, if you did the same thing to the face that you did to the body, and you let it go to custom mode, it will not fire that connect the head to the body node, and the head will disconnect. And I see a lot of people new to MetaHuman animator for the face. That's what they do, disconnects what's going on. So as you would think you would do the same thing to the face of the body, you cannot. You actually have to leave it in animation blueprint mode. The rules are in Unreal Engine, the default behavior is if an animation blueprint is populated there, it will not override it to custom mode, it will leave it in animation blueprint mode. If it's getting buggy, which it does, you would then, well, I would just like delete the whole sequence and start again. That's always a good way to start over. But you would keyframe down that animation blueprint or your custom animation blueprint. Without that blueprint, the head will not connect. This is the core mechanic. But the confusion is that I do this for the body, for the head, it's different. I can see that being confusing. So my last tip here is that UEFN is the UE6 preview. Right? So this is down the road. We're looking at like 2030, where UE6 is going to kind of all become one thing. And so some of the main features, if you've never touched it, it's for games, it's for kids, it's for apps. Perhaps not the Fortnite full BR version of it, but when they have it separated, I've been looking at this and wanting this type of stuff forever. So if you just said UE6 features up there, right? Native source control, amazing. Remote multi-user, if you've ever tried to set up remote multi-user on your own in your own Perforce server, I would love to not do that if I could get away with it. It's going to cook all your content for all the platforms, so much of the stress that I go through getting it on the iPad, the iPhone, console, good luck getting it on console. I guess you're making apps. Xbox apps, maybe not the most common platform, but you could in UEFN when this comes to UE6. Xbox apps, who knows, that's the next wave. Player stat recording, it has an account already, the credit card's in there, payments, all that stuff, pretty fluid. This is being hosted on Epic's Amazon Web Service build, not mine. Lovely, if it blows up and we have all these customers and all these transactions, I'm not paying for that, that'd be great. Built-in system and content, all these pawns that I'm programming and whatnot, to some degree, everything's been done already, and you could probably use a pre-built system to at least get the beginning of your system. Why spend so much time engineering it? There's a lot of nice things in here if that just said UE6. So since the UEFN alpha, I've had this vision. I've sort of understood like I would like to build this ecosystem. Right now, it's tied to the Fortnite Battle Royale. But everything I build is Fortnite compatible as it is now. And the feature set, it grows, and how that stays compatible changes over time. But my MetaHuman systems I build out, the clothing, the cranes, the animations, the camera rigs are skeletal mesh control rig. Control rig, Niagara are the really only kind of like programming animation tools we have at the moment. It will get better. But everything I've been building for these apps is actually full Fortnite spec, down to the Fortnite grid. I build 512, 512, 384. All of this drops, boom, right into Fortnite the second I want it to. It will work. It's very unlikely UE6, when this comes out, will require the Fortnite grid and restrictions that are around it. But you never know. Fortnite certainly is a large driver of the direction of Unreal Engine development. So for me, I'm playing it safe. Everything I build for UE5 is basically UEFN, and I'm going to continue building it that way. And this is me getting some of my assets and rigs ready to build some stuff in the UEFN side of it. So that wraps it up for this. Thank you for coming. And again, if you take nothing away, if you have an idea for an app, go make it. Get a community going, and it could certainly turn into your career. UE5 is a great place for doing that. Thanks for coming. Appreciate it.
So, hello everyone. My name's Chris Murphy. I am a senior tech artist at Epic on the DevRel team. I'm going to preface this with a little bit of an apology. Getting hit with jet lag, something fierce right now. So, the worst thing you can do with jet lag, I think, is then go do a bunch of math. Do you think you're here for VFX? No. No, it's just math. So this is going to be a live build, because I'm not a smart man. We're going to be building things, but I really want to be clear on what today's session is in all of its roboto glory. Today's session is not going to be building a really cool explosion. It's not going to be building a really cool anything, actually. But what it is going to be doing is showing you a bunch of things that make a difference. And I'm going to do a little bit on Nanite tessellation, and displacement. But honestly, the bulk of this is going to be looking at some other concepts. I'm going to be looking at simulation stages. I'm going to be looking at particle readers. I'm going to be looking at grid collections. And I'm going to be looking at neighbor grids and data channels. And the funny thing with all of those topics is they're really, really useful for artists. But they also really sound like they were named by engineers. And the problem with that is when you hear these things, you're like, oh, data channels, why would that be useful? Why would a grid collection be useful? So today is going to be a bunch of simple demos. Of me building stuff, explaining how these concepts work. I'm trying to make it as digestible as I can, because ultimately, when I see people using Niagara, 99 times out of 100, they're still using Niagara like Cascade++. You know what I mean? Like for any of the newcomers, Cascade is UE3's and early UE4's particle system. But they're still kind of using it in the same way. And there's a lot you can do in Niagara that's just drastically removed from that. But awkwardly, folks just kind of don't know about those things. So let's go make some video game stuff. OK, so what I'm going to do is I'm going to start with grid collections. And the reason I want to start with grid collections is, grid collections and sim stages, is I think these are one of the things that is it's a little of a gateway to advanced Niagara usage. I think it's a good place to start. I'm going to go ahead and I'm going to spin up a new Niagara emitter that's going to be a fountain. And I'm just going to call this like NS fountain. OK? Nothing too fancy about this. But what I want to do is I want this to have particle collisions with the world that are going to be a little bit different. I want to get this, and I want to have a big old plane underneath it, whereby anytime those particles touch that plane, I want to leave a mark. So I kind of want to paint onto it. So we're going to be spraying particles in the air that whenever they touch the surface, I want to leave a mark there, right? And, And to do that, what I'm going to do is I'm going to go ahead, and I know that if I want to paint onto anything, I probably need a render target. So I'm going to start with that and just call this RT underscore impact paint. Cool. And I'm just going to drop that straight on. I know, I broke the rules. I put the texture straight on it. OK, so we're going to be painting impacts from this fountain into here. Here's where we begin. So with this system, we have a basic fountain, nothing fancy about it. But what I want to start with is over here. You've got an emitter spawn, which calculates what happens when something spawns in the emitter. Update is as the emitter is updating, it's the logic it processes. Particle spawn is the logic that the particle does when it's created. And then you have particle update, which iterates over all of the particles while it's running. I'm assuming everyone pretty much knows this at this point, right? But if I click, first off, turn this into a GPU emitter. But if I go stage, add stage, this creates what's called a simulation stage. And a simulation stage is a really fancy way of saying we're adding another update loop. So after it's run that update loop the first time, it's going to run another update loop that goes through everything again. Now, by default, that runs through all the particles again, but we can actually run that update loop over anything we want. So think of it this way. If I was to say, hey, when this emitter is created, I want to spin up a new variable, and that is going to be a grid 2D collection that I'm going to give the name myGrid, or gritted, apparently. Hang on, let me just fix that up. I warned you all about the jet lag. All right, so we've got myGrid. Now, a grid collection is essentially a 2D array that just holds whatever information I want to put in it. So it's storing it on an x-axis and a y-axis, okay? And that information, if you think about it, what I'm actually going to do is my grid collection is going to represent this render target. Just imagine that you were laying like an Excel spreadsheet over the top of that thing, and every time one of those cells was being calculated, it was like, how close am I to the nearest particle? And based on its proximity to the particle, it'll paint a color to be like, am I being hit or not hit? So I've created a grid collection. While I'm here, I'm also going to create a particle attribute reader, which I'm going to call myReader. I like giving them the word my, personally, just because I can really explicitly see that it's the thing that I created and not something auto-generated. Weird habit. So I've got myGrid and myReader. Now, a particle attribute reader is a way for any system, including itself, to analyze particle information inside of that system. So if I have a reader, I can actually have something else analyze where all of these particles are and then chase those particles, for instance. Or in this collection, my grid is going to read the particle information to find out information about it and know what it wants to do with its life. So I'm going to give this a name just for, I'm going to call this like render to grid. And I'm going to go ahead and add a function to it. OK, and I'm going to add a scratch pad. And I'm going to call this draw to grid. All right, so within here, this is the logic we're going to process for every single cell as we iterate through it. And to show you what that looks like, I'm going to get a reference to the grid. And just as an example, I'm going to get execution index to unit. I know I'm going quickly, but oh, I've got so much ground to cover. So here's how this works. You'll see this phrase thrown around a lot, to unit. Anytime you have a grid, be it 2D or 3D, to unit means show me what the grid coordinates are between 0 and 1. So if I have a grid that is 512 by 512, then 0, 0 is a value of 0. 512, 512 is a value of 1. You know what I mean? It's kind of normalizing the grid. And the reason I'm doing that is because this will let me kind of like draw the UVs. I'm just going to draw the length of the UVs or something here. And I'm going to output that as a value that I call distance. Now, the next little thing I'm going to quickly mention here is that anytime you have an output value that is stack context, it means that if you use it in a particle, it will save it as particle.distance. Anytime you use an emitter, it'll be emitter.distance. But when you use it in a grid, it will now actually save this variable to the grid as like the grid's information.distance. Cool. So that's plugged in. We're not quite where we need to be yet, because there's one other thing I need to do, which is after I spawn the grid, I need to set the resolution. Now, I typed in set resolution, and we saw nothing. And the reason for that is most of the grid behavior is not in the library, but rather when I turn off the library, we have a ton more grid stuff that we can use. So I'm going to get that. I'm going to set the resolution of my grid. You'll notice at this point that a lot of what I'm doing is a little bit boilerplate, unfortunately. So we have a 512 by 512 grid, and I'm just going to preview that on there. Now, it's still not working, and the reason it's still not working is this last little bit, which is before I said that this is a separate update loop that iterates over whatever we want it to, I need to actually tell it what we're doing. Right now, it's iterating over all the particles, but I'm going to say, I want you to iterate over my grid. Now, it's OK. The biggest mistake, easiest mistake, most frequent mistake, I should say, is anytime you create a scratch pad, you've got to remember to bind your variables to the things that you created inputs for. But interestingly, that's now got a black to red value. Do you see that? Because as the unit is moving further away, the length is getting further. So I kind of just drew a little spot. That's nothing impressive. But what is good about that is that we now know that we can render information to a render target. And we know that that information can be used, right? So now that I know the grid collection is there, I'm going to do some quick math. And I'm actually going to remove you. What I'm going to do is I'm going to really quickly do some math to just calculate the position of where this render target is. 0 to 1, 0 is the top left corner, 1 is the bottom right corner, right, on the UVs. However, we're offset because the pivot point is in the middle. So you don't need to know how to do this bit. I'm just going to gloss through it. But if I subtract 0.5, it's going to offset the circle to the center. If I multiply it by, I think I scaled the thing up by 4. So if I multiply it by 400, that should now give me negative 200 to 200 in my local space. Again, you don't need to know how to do this bit, but I needed to show it to you. That's now going to give me a vector 2D, which is like the x, y coordinates. And I need to have x, y, and z. Sorry, no, yeah, x, y, and z. Z. So I'm just going to really quickly, you can do that to me. If I can spit, position. There we go. All right, we got there in the end. Sorry. So I'm just doing this real quick because what I want to do is convert that from two-dimensional to a position in space, and then I want to find where that is in the world, which means I'm going to transform it from local to world. Again, this is really quick. And the next thing that I'm going to do is going to be far more interesting. I'm going to bind this to a value that I'll call like cell position. OK, so here's the next bit. What I need to do next is I now need to look at this position, which is I now know where it is in space, right? But I need to look at that position and compare it to a particle location. And this is where a lot of people are like, well, I guess I need HLSL. Because I need to iterate over every particle and find out where they are, right? And then calculate it. Cool little thing you can do is not use HLSL, which is if I was to get like the particle reader. Sorry, I'm not used to this keyboard and it is messing me up. There we go. If I was to get a particle reader, normally what people think they need to do is write custom HLSL. And as a heads up, you can write your own blocks of code here. Cool thing is you can actually right-click on any interface, and I can like click that and then paste in the function names and stuff like that if you don't know what the HLSL functions are. But I also kind of hate writing stuff in HLSL. I think I'm just well and truly on the node train at this point. So what I would actually suggest doing instead, if you're someone like me, is we have a thing called a map4. And the map4 is great because everyone tells me it doesn't exist. What it is a for loop. You can run for loops in Niagara, except they're backwards. So how a for loop works in Niagara is it starts here, and then it rolls back to the last time you had a map set. So the last time you set variables, it just cycles between those things, if you get what I mean. So that kind of controls the space of a for loop. Anyway, I need to run this for every particle. So I'm going to find out the number of particles. And now for every particle that's there, I'm going to go ahead and access that cell position that we got. And I'm going to access the position of the current particle that we're examining. Now, this literally lets you look at any attribute that is stored in that particle, like the particle reader, any particle information. So I can look at the position of the there we go, of the current particle. And in theory, what we have on screen is that will give me the information of the first particle, the second particle, the third particle, the fourth, fifth, sixth. And I can just do a normalized distance. You're here somewhere, I'm going to find you. Range. Sweet. All right. So this function looks from this location to this location. And if they're more than 100 centimeters apart, because it's set to 100 here, sorry, Unreal units, what it will do is it'll be a value of 0. If it's within that, it'll become white. I'll show you what I mean. If I go this value and just plug that in, I'll call that distance again because I kind of like that. And I change the namespace to here. what that should do, once I remember that thing that I said everyone screws up, you've got to plug it in. All right, see that little red dot that's bouncing around now? That's because every one of these is saving over the previous particle, right? Like I'm not grabbing the highest value that it's been. That's okay. I'm literally just going to say, hey, look at the value that's there. But this time, let's access the current distance value that we've got. Sorry, I know this is getting a little bit cluttered. I'm like, yay, nodes, and then I show you a mess. But I swear it's normally a little bit better when I'm not standing in front of 500 people. Okay, good. All right, just go down to the max value, ship it. Oh, apply. Okay, you will always get this error. If you ever try and access a value that you've never given a value to, it's going to panic. It's okay. Just literally click the value and be like, it's okay to be 0. All right, cool. So that is now saving all of those positions as they kind of stream out, right? What I'm going to do, just to make this a little bit cleaner, is I'm not just going to access the particle position. I might as well also access the sprite size. Oh, I hit the wrong one. There we go. Vector 2D. Yeah, cool. Sprite size. Now, sprite size is just a 2D vector that gets stored in every sprite. And if I get the length of that, and I make that the distance, that should now be the same size as the particle. Yeah, cool. So now that that's done, save. I'm just going to do one last little thing, which is simple, which is I'm going to create a user parameter that is going to be my render target texture, RT output, seems good. And that's my impact paint that we created just before, right? And with that in, my grid, render output to that. Cool. So now anywhere they're hitting, they're now kind of saving that information off. You get what I mean? Now, I wanted to show you this. I know it's not super fancy, but I wanted to show you this because I really want people to start understanding that like we can handle collections of data, we can process particles in a different way. And now this is a gateway, right? Because if we think about what this could be, I'm going to skip some stuff and come back in a second. Oh, eye adaptation. So see these clouds out here? These clouds are actually a Niagara system that's painting. This here is the output, where it's a circle that's gradually moving around, painting clouds into the world. You know what I mean? Like, you can grab your Niagara outputs and feed them into all sorts of other data and make some really interesting effects. I can have them feeding clouds, but I could also have them working on more advanced effects. So really quickly, like if I was to come over to here, so Nanite displacement is a feature that we added in 5.5, right? Well, we added it in 5.3 and didn't really tell anyone, but it's stable in 5.5-ish. So what's going to happen here is Nanite displacement allows you to have these like offsets of values, right? So in this situation, if I was to look at this material that we've got the bumps going on, Nanite tessellation, all that's going on here is I'm reading in a displacement value onto an offset, which is kind of giving me this. If you want to get this working on your material, you just need to make sure that enable tessellation is set up. And if you want to control how far out it goes, you do that by setting the magnitude value in here. Honestly, it's pretty straightforward. Amusingly enough, the biggest gotcha involved is you need to make sure static lighting is disabled if you're doing it on skeletal meshes, which will cause a crash in 5.5 preview 1. It's fixed in main. It should be fixed in 5.5 preview 2. But on static meshes, it should work out of the box. So I bring this up because Nanite displacement, sorry, my eye adaptation is gross. There we go. Yeah, cool. Isn't that nicer? All right. I bring it up because you can use a texture mask for a Nanite displacement to start doing things like this snow, okay? Which is cool. But I wanted to make sure that people were aware of another really useful thing, which is if I look at this material, I have a mask. This texture object here is called Mesh Paint Texture Object. Mesh Paint Texture Object is honestly probably the coolest feature we added in 5.5 in my opinion, like for all of the other cool stuff, and it sounds so dull. I accidentally had two of them in the same space. All right, here's what it does. If I go Mesh Paint, and I click on this, actually I'm gonna go I'm going to remove everything. So by default, this is what you're going to see. But when I go texture color, add, I'm going to crash. All right. That's pretty funny. All right, I'm going to try that one last time, and if it doesn't, I'll move on from that. Real shame, because it was definitely working non-stop. All right, so mesh paint modes, texture color, that's okay. I'm going to go with the one that I've already added to it, but I will fix this eye adaptation again, because it's just hurting me. Okay, cool. Mesh paint mode allows you to paint straight onto the mesh. Shift click, left click. And it will actually save. This is something you couldn't do with Nanite meshes historically. So you can have like a statue in there and comfortably have like 30 different differences between different assets that look, they're still using the same mesh, but you can bring in like inherent variation. It's really something folks need to get on. Usually you click add and then you paint. The remove button did not work for me just then, so we'll all back away slowly. But there's no difference between what I'm doing there and running my particle system. Like I know I'm projecting them up into the air like a fountain, but like conceptually speaking, this here is able to now paint onto a surface, right? This could be a mesh. And I bring this up because if we know that we can paint that kind of mesh displacement and fun stuff through render targets in Niagara, we can couple these things together. This is where tech artists and VFX artists truly shine, is like how do we like get these two things together and make them stick together. So we've got weather simulations as an example of things that we can do, but what I'd love to do next is I want to spin up a new, sorry, I've lost my content folder when we crashed. I'm going to dupe that and call it ns_character example. Yeah. Cool, so character example is going to be something similar, except this time around I'm going to get a friend of mine called Quinn. And what I want to show you is this. So I've got Quinn, and I'm going to use her as the thing that I'm painting onto. I'm going to grab a Niagara system, spin that up, and I'm going to throw that in. What did I call it? I called it character or something. Yeah. All right, cool. All right, so we've got this character in there. The next thing I'm going to do, just really quickly as we kind of get this set up, is I'm going to spin up another render target. You can dynamically create render targets from Niagara. You don't need to create bespoke ones, by the way. So don't stress about that. But I'm just doing it so you can kind of see this setup a little bit clearer. All right, my character example is still my fountain. I'm going to change the user parameter for my texture output. That's weird. OK, it looks like when it crashed, we lost my user output values. That's fine. I don't think we lost anything else in the process. I guess we'll find out, huh? Cool. Sorry about that. I'm just trying to catch up from where we were in the crash. Threw me a little bit. All right, so I'm going to output to this character texture mask instead this time. And I'm going to make sure you're correctly plugged in. So I can see that's working. It's saving to my texture. What I'm going to do instead, sorry, Quinn. What I'm going to do instead is I'm going to get this material and apply it to there and apply it to there. And I'm going to change one thing. Ahead of time, I changed Quinn to have an extra set of UVs. I set her UVs up to be UV1. Okay? So what that means is the material that got auto-generated here needs to preview on UV1. So I did that so that she had like unique UVs instead of any mirroring or anything like that going on the character. But what I'm going to do instead is over here, I'm going to spin up a new user parameter that is a skeletal mesh reference, and I'm going to call it my mesh. Cool. So my mesh is going to be there, and in my draw to grid, what if I just ignore everything I did here, but instead we access the skeletal mesh, and we say, hey, this here is a UV. Remember, we did 0 to 1, basically, in the grid. We iterated through it. Conceptually speaking, like, there's no difference between getting that and like finding out which triangle is at the current UV index that I'm looking at. And this will actually tell me where on the character it is. And if I know where on the character it is, I can then take the next logical step, which is I can look up the triangle data in world space. And this will tell me the exact position of that current UV that we could be painting to on the character. Cool. So why that's good is this, so you're in. All right, cool. So I need to do one other little change. It's still painting, but now it's getting a bit weird. The reason for that is whenever you bring in a mesh like this, you need to make sure that it knows which UV sample it's referencing, which in this case needs to be reference 1. So reset that. Good. Okay, give me 1 sec here. I'm like, why is this not referencing? It's because I did the thing that I said everyone screws up, and then I just demonstrated that to you again and again and again. All right, so that actually is working. I'm going to shrink the particle size down so it's a little bit, let's go to 10 just a minute. Let's also maybe, we've got a sphere shape location already. I'm feeling like if we put this above her head, slightly forward, you can ignore this part. I just want to create some vague sense of snow or something. Get rid of the add velocity. Yeah, reset. Well, messed something up. Did I double type a value without realizing it? Track sets. Gonna go back to you. All right, sure, why not? Oh, that's why. I did it as a position offset instead of a, and none of you told me. Yeah, good. All right, so that is actually working. You can see as those particles are kind of falling through, they're painting the surface of the character now. And if I was to shrink this down to have little small particles, that should be a little bit more evident. All right, and obviously I would want to normally destroy these, and I might actually want to iterate over the previous frame, so I did kind of like a paint between the two locations, which is why we're seeing that circles. You can do that later. What I care more about right now is if I was to do this, but I wanted to have like 5,000 particles, this gets out of hand really quickly, and not just because like she's now being showered by snow particles, but it gets out of hand really quickly because if we're doing 512 by 512 and then we're multiplying that against every particle, you're going to have a bad time, right? Especially like as this number increases, as the life of the particles increases. And that's why the next thing that I want to do for the next, I got just enough time, this will work. Next thing I want to do is neighbor grids. So neighbor grids are a really interesting thing that we added that are super useful that no one really knows about. Let me tell you. How it works is we can create a grid around the player or the emitter that is 3-dimensional. And what happens is in every single grid cell, they store one thing. What they store is which particles are also in that grid cell. Does that make sense? So we have a whole bigger, like a whole 3-dimensional structure which says this is which particles are near me. Okay, again and again and again. And you're probably like, why does that matter? And that matters because right now I'm iterating through every particle, right? But if each UV cell was able to say, which grid cell am I in? I'm in this one. Cool. Which particles are also in that grid cell? Then it means each grid cell only needs to iterate through the particles that are nearby. You know what I mean? Like we've created a local check for these things instead of checking every particle. Yeah, great. So I bring that up because grids, again, like you hear the word neighbor grid and it just doesn't sound like a good time. But if we create one of these, which I'm going to have there, I'm going to call it like, it hurts me to write neighbor without a U, just for the record. So I'm going to create a neighbor grid. The biggest trick is that the neighbor grid needs to have some kind of attributes set for it. So first off, we're going to set the library only strikes again. Sorry, folks. I really should have had more coffee. Neighbor grid 3D set resolution. Which grid? Whatever I called it. Actually, I called my neighbor. Oh, that's going to come back for me. All right. We can set this up however we want. Like you set up how many cells you want. So I'm going to be like, hey, look, we want like, I can reliably say there's probably not going to be more than 30 particles per cell. And you want your cells to generally be big enough to encapsulate an entire particle. So I'm going to just pick a number out of thin air and say 30. Why not 30, 30? OK, cool. So with that in, we now need to have the extent. The extent is going to be like, well, how big is the grid? I'm just going to eyeball it here and say 200 by 200 by 200, which gives me a 2 meter, 2 meter, 2 meter. In fact, it's good to push that off to a user variable, so it's something that we can tinker with later. So in theory, that gives me a hypothetical grid construct. Now, that grid has no place in space. It's like it's the concept of a grid and the data storage for a grid that could exist, but it has no like way to figure out where something is within it. And that's where a really common function that we use a lot here, which is units to world transform. What this does is it literally says, based on this offset, which is my simulation's position, and based on this rotation, which is going to be my simulation's rotation, and these extents, which will be the things I just pushed off to a variable, that is how I will define this grid. You know, if something says how big is the grid, this is what says that. All right, I know this is in-depth, meaty stuff, and you're expecting explosions. My apologies, but it's every YouTube video out there shows you how to do cool explosions and things like that. I really wanted to focus on like the parts of Niagara that people just don't know about. I want to push people further where I can, right? So we've got that. We can see the grid. I wanted to skip 5 minutes of this presentation, so I added something to the engine, which is pretty useful, which is this neighbor grid 3D visualize function. I'm just going to make this function. I'm going to call it visualize grid. And this needs to know how to define the unit to world, which is auto-created by that function from before. It needs to know which grid we're iterating over, which I called my neighbor and didn't add the word grid in, and I've regretted twice and used it twice. Now, that is already working. It's painting the bounds of the grid around the character. Do you see that? So that's where the cells will be. What's really cool about this function is if I go to particle update and I say populate neighbor grid, which needs to know unit to world, and again, neighbor, spelt wrong. That should, oh, and last but not least, iterate over the grid data interface. Cool, save. I hate that that's probably it. Nope. Sorry, folks. Give me just 1 sec. First off, I'll visualize empty cells. Yep, that's working. We are populating the grid. We're setting the resolution. We're iterating through it. That's all getting put into there. Neighbor grid position is reading. Position IDs is reading. Let me just verify it's not that. 5 points for whoever can pick what I've screwed up. Unit to world, unit to world. Simulation to grid unit. Oh, yeah, good. Sorry, I translated it from one space to the other incorrectly. But what that's actually doing now is that is actually forming a little grid cell around, around each of these, which is adding it, which is nice. There's actually, I realize I've actually made another mistake, but that's fine. So that's actually putting every cell, it's figuring out which grid cell everything's in. Do you see that? So like those little grid cells that are green are the ones that have data in them. Yeah? Little mistake that I just made is this function, there's a better one. And that is actually called fill grid 3D neighbor. Sorry, that's why I was thrown before. I'm like, why is this looking weird? And the difference between the two is that added everything to one grid cell, right? But this one does this. Now, what's interesting with this is actually finding the surrounding neighbor cells. And the reason that's more useful is because that way if I'm in this grid cell, but I'm overlapping these ones a little bit, it's still querying that. So it's actually giving it more information that they may need to query, but it's more reliable because you don't get like weird transition of grid cell issues, right? Anyway, last little bit that I want to have there is with this in play, my draw to grid function, if I wanted this to use grid cell information instead, there's a bit of legwork here. I'm going to do it, and then I've got 5 minutes to do data channels, which will be fine. I'm not busy, you're busy. Okay. So I'm going to access my neighbor grid, and I'm going to find out where my neighbor grid is. So I want to get the, all right, this is a bit of logic to step through, and hopefully you can look at the YouTube video later to work this out. But I'm going to get the current position of the data cell that we're looking at, and I'm going to do a matrix transform, which is definitely one of those things that sounds cooler than it is. I'm going to transform that position into my grid logic, where it represents 0 to 1. To do that, I need to read in a matrix, put on my favorite sunglasses, and I'm going to call this world to units. Again, I don't really expect people to go home and just immediately smash this out, but I do think in a perfect world, some of these strangely named things in Niagara make a little bit more sense to you. And that's the starting point for some of these things. So I've got index, and I'm going to cache off the index to a linear. Now, all that means is this is figuring out what cell it's in, like X, Y, and Z. Linear is kind of like, imagine all of those rows were stuck one after the other and stored in like a big single line. Sometimes you need to look things up through a linear index. Sometimes you need them through an X, Y, Z. It's just how it be. But I'm going to grab this linear, push you off to here, and I'm just going to call current linear. All right, whatever, linear. Okay, sorry, we're running out of time, so I'm like, okay, cool. So with that in mind, we're almost there. I now no longer want to iterate through every particle. Instead, I want to get the grid, and I want to get my neighbor grid. Whew. And I want to get particle neighbor count. So that's saying how many neighbors exist inside of this grid cell. I actually want to get the smallest number between either the neighbor count or the max number of things you can fit in the cell. Weird quirk of neighbor grids is, you know, before I said no more than 30 cells per, no more than 30 particles per cell. It will actually keep counting once it goes over 30. So you need to tell it, you know, chill out. Just give me the ones that I asked for because we don't want to mess that up. But in technical terms. Cool, that should now iterate through every particle in the cell. And the last bit that I need is, and this is again a little bit of legwork, but I care more about this conceptually, is now that I have this grid, I want to access this one, cool. This takes an X, Y, and Z, and then the neighbor index. It then tells you what that is inside of the particle reader. Basically, this transforms all of that data to be like, this is the particle that you're after right now. And what that means is if I was to access that linear value again, need coffee. And I was to go linear to index. Again, a little bit janky. X, Y, Z. And this was the current iteration. All of that together didn't really get us very far. In fact, we're going to see the same visual result, right? But this is the difference between someone on YouTube saying, yeah, but that won't run on your computer, versus, yeah, well, sorry, do I sound bitter? For the record, actually, I'd like to get this out there. Every demo I've put together in the last quite a long while was done on my laptop. And every time, without fail, someone on YouTube says it requires a beast computer. And I've been like, oh, no. All right, world to unit. Great, great, great. Cool. I'm missing a value somewhere, which is why we're getting that clip. Oh, sorry, wrong function. Actually going to turn off the visualization. Sorry, folks, I've missed one value somewhere. Get particle neighbor, iterate through, calculate linear. Linear is getting the particle count. That's stepping through. What am I missing? It's giving me the same picture every time, which means it's giving me the same grid cell every time. If it's giving me the same grid cell every time, then what we're looking at is probably screwed up here. All right, I'm going to solve this in either 1 minute or not solve it and move on to the next topic. We're very close though, so I'm really suffering here. Position of vector, world to unit, min. Sorry about this, folks. Get the particle neighbor count, get the max per cell. Everything seems fine. What am I doing wrong? It's grabbing the interaction, but it's painting the wrong particle. Well, that's embarrassing.
Is it getting to the neighbor grid part? It looks like it's stuck in the cell and not getting the next cell.
You got it, you got it, you got it, you got it. Yeah. I think what you've done is, I'm iterating. When I changed this, I think oh no, nope, take it back, don't got it.
Keep it in.
You should keep it. All right, look, I'm running out of time, so I will jump to the next bit. Damn, I do have a working version of this that I'll throw up on the dev community later. This was me just crawling particles over her as necessary, and I can put as many of them in there now. With a grid setup, you can push it up to like, I've had 5,000, 6,000, and it's been fine, which is really cool, because you're able to kind of like split this out and just massively work this out. But I want to point out that when you're using this kind of logic, there are some really good examples that hopefully inside of the Niagara content examples make a bit more sense. Like the particle reader is being used here with sim stages so that these particles stick to one another, find the nearest one, create a structure, and then that structure is then used to like split them apart. So you've got this like cool kinds of setups. But there's some really, really good Niagara setups that you can go through in the content examples, but no one really knows how to understand them. Like they're too complex to really get the foundations, which is why I wanted to step through grids. I wanted to step through neighbor grids, and I wanted to step through sim stages so you could start to understand what you're looking at in that demo room. Last little thing I want to do with my remaining 7 minutes and 20 seconds, here we go, is data channels. So I created this scene, and I present you a problem. Actually, it's great, but the problem is this. If I have a game where I'm spraying bullets at a wall, and we're getting like impact effects coming off of it, right? Often I would be spawning a new impact effect for every impact on the wall. You're all still with me? Cool. The problem with that is if the front row joined me in and we were all shooting bullets at said wall, really quickly we have just a gross number of impact effects that are going to be spawning, right? Problem. So what we actually have is a cool system that no one knows about, but if you spin up a data channel, just going to type it in here. And I'm just going to call this impact example data channel. And I'm also going to go ahead and get the impact effects we were just looking at, that like pew pew. Copy here. And I'm going to rename this to be like impact data channel. this system is now going to be leveraging that. So here's how this works. Inside of the blueprint for this ship, instead of the ship creating a system at that location, we're going to do something different. Actually, I'm going to set up the data channel first. My apologies. So a data channel is a way of kind of pushing off a whole bunch of data and then accessing all of that data in Niagara. So I'm going to create a data channel island setup, and I'm going to add some variables to it. Position, which is going to be of type position. And we're running out of time, so I'm just going to do rotation, which is going to be a quaternion. Don't worry, it'll auto-convert. Now, the other thing that I'm going to do here is aligned static is fine. What this actually does as a system is Unreal says, in this case, 5,000 by 5,000 by 5,000, but fuzzier. What's going on with that screen? It will actually say, is this emitter playing within a 5,000 unit square? Yes. If so, grab the effect that's coming in and stuff it into the existing emitter. Does that make sense? So all of the ones that happen together in that single area can get batched together, which is really useful. So if I come back here, I can be like, all right, so I want to have that. I'll set that up as aligned static. I'm actually going to turn on the debug as well so you can see it. But in my turret actor, instead of creating a system in the way that you would expect to, I create a data channel impact where I read in the position and I read in the rotation. Told you to auto-convert. Right, so that's now going to be the position of the effect and the rotation. I'm also going to do a search parameter. Search parameter is like how do they get batched? And you can batch them by component, which is cool, or you can just batch them by location. I'm going to do location so that they all kind of get put into an island together. Now, if I was to close this, I haven't set anything up yet, so this is all still wrong, but if I was to close this, with those debug values on, we can actually see that these are the islands of where those effects would have been spawning in. So this would be spawning 2 emitters. I didn't show you before, but it was spawning 230 effects or so, because I'm deliberately firing a whole lot of bullets. In my data channel, I'm going to tell it that what I want this thing to do is to spawn this system, which is right in front of me. System. Sorry, folks. Right. There, system. Sorry. Like I said, coffee. Data channel. Great. All right, I'm going to do this as quick as I can, just because we're 3 minutes out from time. My data channel system looks like this. First off, I need this system to now run infinitely. However, I want to complete it if no effect has been spawned in the last 5 seconds. Okay? In this system, I'm going to tell it that I want it to be based on the I want the emitter state to just do whatever the system is doing. I get rid of spawn burst instantaneous. And instead, in my emitter spawn, I'm going to have a new scratch. That was a funny story. Sorry, folks. I want to have a new variable. New variable. I just did it twice. New or existing parameter, which is going to be a data channel reader. By the way, you can write to data channels from Niagara, which is cool. I'm going to have this reader, and what it's going to do is, instead of spawning the way that we usually do, I'm going to actually create the scratch pad that I really wanted this time, and I'm going to call this like spawn from data channel. It's going to have a reader as an input, which is basically going to get that, and it's going to spawn conditional. So it's kind of going to be looking at that system, finding out what it needs to be creating, and spawning that many particles, which in this case, there's just a little bit of boilerplate. Hey, is there a session immediately after this, or do we go to lunch? All right, you're stuck with me for 2 extra minutes. Sorry, am I threatening you with a good time? All right, so that's in min spawn, max spawn. That's all I really need to do here, okay? And then over here, where I'm initializing the particle, I'm going to, instead of setting the position here, I'm going to create a scratch pad that I'm going to call like initialize from data channel. I'm going to capitalize that C or we're living in anarchy. That's going to be a data channel. And I need to access the spawn data. There we go. And then I need to read. And if I select the one that we've got there, that now feeds me the position and the rotation information. Do you see that? And I can just pump that information straight into the particles that we're about to create, right? So I can set particles.position to be this position. The rotation, I'm just going to push off to here, and I'm going to call it like spawn direction, I guess. Apply. We go back to here, and I make sure that everything's actually set up with my data channel, because I apparently learned my lesson. 50 to 200, I guess. Still getting a failed here. What's failing? That's fine. Initialize some data channel, compile error. Sorry, folks. Just seeing what my log is. This is going to be. Oh, yeah. Sorry. I didn't read in the emitter ID. It would help if you plugged it in. And this is the execution index. All right. Video games. OK, cool. So that's theoretically fine. Just because of paranoia, I'm also going to set some bounds so this thing definitely renders where it should. Might be fine, but I have trust issues now. I feel like I let you all down on that previous effect. I don't know what I did wrong, but I didn't have time to check it, you know? Cool. In theory, that's fine, though. Yeah, sick. So that's doing the same thing. Before, that would have been 200 and something effects, except now, if I go stat Niagara, we're sitting at 30. And I bring that up because another cool aspect of this is this stuff can all be made from within Niagara as well. So you can actually have data channel information spawning from other places and feeding in effect data. If you look at things like our volumetric effects, so when we're doing fluids and stuff like that, instead of creating 100 fluids, which is really intensive, you could use a data channel to inject all of those fluids into a single fluid emitter that's in the correct region. Do you get where I'm coming from here? See why this is really valuable, but again, it's just kind of one of those things that's both really valuable, but just really not well known. So my apologies for running a little bit over time. Hopefully this session has been useful for you. It's been a little bit erratic, and God, I need some coffee. But thank you all very much for your time. If you have questions, I'll be floating around for the rest of the event.
Welcome to Myth-Busting Best Practices in Unreal Engine. I am your host, Ari Arnbjörnsson. And just a little bit before we start is that I just published the text version of this article just now. So if you'd rather not sit through my antics, you can just leave and scan this. Don't leave, please. No, it was a joke. Or you can search Myth-Busting Best Practices in Unreal Engine online. It should be indexed already, or just go to Ar.games, it's at the top right there. You can share this with your coworkers. So I'll give you one more second. Yeah, best practices. You noticed I put it in quotes, best practices, so-called best practices. The thing about them is that many of them are true. They come from some source of experience, but the thing is many of them are also bust. But in all cases, you need more context. And that's what I'm trying to give you here today with this presentation. I'm trying to give you more context to all of these things. So actually, I want to play a game, and you are all invited to play with me. We're going to play true or bust. Woo! I will ask you, we have 9 myths. I will ask you which one says this is true? Which one will say this is bust? And I want you all to raise your hand with whichever one you think is true or bust. And I know, many of you are like, it depends. Boring. So boring. I am always going to pick either true with a little like asterisk, but remember, or I'm going to pick bust, but I'll always say a but. But I'm not gonna go like it depends, and I don't want you to do that either. So first, I'll give you a myth. I'll explain a little bit about it, and then I'll ask you to pick one. And if I count something that doesn't add up to everyone in here, I will call out the crowd as cowards. You don't want that to happen. But I think you've been good sports so far. So let's see. First myth: don't use tick. Oh. Oh, wait. I'll get there. We're going to do this the scientific way. So first, what is tick for the ones who are like, what's tick? Tick is a function that any object can implement, or actor, to have some code running on every frame of the game. And some people online, or even your coworkers, will say, hey, you shouldn't use tick. I want to see how many people here agree with this. How many people here say, yes, don't use tick? About 10 out of 300. How many people here say, this is bust, you can use tick? Hey, come on, okay. I would say about 90% of you, and there's about 7% here that are cowards. Pick one, come on, it's fun. Anyways, let's talk about tick. A lot of gameplay code happens in tick functions. And the ticks, they only run on the game thread, and it's single-threaded. Tick is powerful, all right? We have the tick groups. You can do something before physics. You can do them after physics. Or if you are not, I want to give a special shout out to during physics. If you are not planning on reading any transforms, or if you're not planning on modifying any transforms, instead of doing your code and then the physics simulation, you can do them both at the same time. Quite cool. You also have tick dependencies. You can say, I myself will only tick after that one actor has ticked. And that actor can have another dependency. So that's quite powerful. You can change the tick interval of any actor at any time. For example, instead of ticking every frame, say, oh, tick only like once every 1 millisecond, or once every 0.1 millisecond. You can change it at any time, and you can also disable ticking and enable ticking for an actor at any time. But the thing is, it does have a slight overhead because of those features. And let's talk about this overhead. It is slight, and it is only noticeable when you have lots of ticking actors. But the overhead itself is usually negligible compared to the work you're doing during tick. And I thought, well, I'm wearing a lab coat, story behind this one. And I thought, let's just measure it. Okay, so this is a little like, this is on my computer, which is a 2.69 gigahertz Threadripper. This is also on Unreal 5.4, so in the future we might make the tick system faster or something, it might not apply anymore. And yeah, so this is tick overhead per actor in microseconds. For your information, there are 1,000 microseconds in 1 millisecond. There are about 16 milliseconds per frame in a 60 frame per second game. So if you start having lots of ticks in your game, it will start showing up in 2 places on the profiler. It'll be the queuing of the ticks. And here we have how much time that takes in the Blueprint editor queuing of it. We have the Blueprint package development build. We have a C++ editor and C++ package development build. And they're all about the same with a little like fluctuation because of profiling isn't an exact reproducible science. But then we have the tick overhead of actually calling the tick itself. And we have the Blueprint editor, which is taking 3.5 microsecond. We have, when we package it, it already halves. So a packaged Blueprint tick in a development build will only take 1.8 microseconds. And then if you decide, I don't want it in Blueprint, I want to convert it to C++, and you only have a C++ function, it will take about 0.6 to 0.7, both in editor and development build. And I know what you're thinking. Yes, I do. Don't correct me. I know what you're thinking. Take overhead, you see Blueprint editor taking, you go like, oh, it's so big. It's a big bar. It goes from the bottom to the top of the slide. It's so slow. But the thing is, I think usually having some context makes this, make a little bit more sense. So let's add some context. So here we have, again, the tick overhead from the previous slide, just overhead, not the queuing. And this is from Lyra. This is from Lyra's player character. And there's a few functions that happens in Lyra's tick function. We have the character movement component, and that takes 241 microseconds, right? Then we have also the player controller itself, which is called in Lyra, and that is taking 125 microseconds. And just those two together, even with the Blueprint editor tick, you know what I measured? I was like, what is the ratio of a Mars bar to its wrapper? And what is the ratio of the tick to those two functions? And the tick is actually lighter than the Mars bar wrapper. And I don't see many people buying a Mars bar and go like, I'm paying mostly for the wrapper. No, and you're not paying mostly for the tick, not in this case. And a little extra case here, you see I add a little extra there. There's the Lyra rifle skeletal mesh. It's taking 20.7 microseconds. And when I saw this on the profiler, I was like, the rifle gun is a skeletal mesh, and I looked into it. It has two animations. One of them is reloading, which the magazine pops out and goes back in. And this one is from when you're shooting. Do you know what the rifle does when you're shooting? The barrel goes like, the tip of the barrel goes like this, a little bit. 20 microseconds, 0.7. And you don't see anyone shouting like, oh, the rifles in Lyra are too slow. No, and you shouldn't be doing that about the tick either in this case. However, of course, it depends. Because if the tick is doing less, let's say the absolute worst thing you could be doing is that you could have an empty tick, because then you have nothing but overhead. And if you have 1,000 actors with an empty tick, well, 3.5 microseconds times 1,000 is now 3.5 milliseconds. Now it's a chunk of your frame time. So how can you avoid an empty tick overhead? First, we have here just don't have a tick function. This is in Blueprint. So if you just don't have a tick function, no tick overhead. Don't worry about it. If you have the ghost tick function, don't worry. Ghosts aren't real. It doesn't tick. But the thing is, as soon as you connect that event tick, it materializes into a real tick function. And if you later decide, never mind, I'm not gonna do that, and you disconnect it, the tick is still there, even though nothing is connected to it. It's still materialized, and this actually is an empty tick function, and it will now take 3.5 microseconds of just pure overhead. People have there's different ways to find this. You can make an asset validator. It shouldn't be that complicated. I actually tried making one, and actually, yeah, I'll add it to the article, the validator, so you can check it in your project. Funny thing is also the Blueprint compiler will decide whether it enables tick or not, and we could just add it as a check in the Blueprint compiler, hey, if the tick isn't connected to anyone, maybe just treat it as it doesn't exist. This is for our engineering team. Let's fix it. I have a comic for you all. Let's say you're doing some blueprints. Maybe you're a junior programmer or a game developer doing some blueprint. You're setting some stuff. The game is running really well, 120 frames per second. Nice. You are like, oh, let's put a sequence here and there. Let's do some uncomplete, do a little bit more. Time is going up a little bit. Well, let's get all actors of class. Let's put some more wires in there, right? Connect some more nodes. But eventually, you might start wondering, why is it so slow? What's happening? And someone who's experienced might walk by, or might talk to you online, and they have only time to say this one sentence. They go like, I've seen this before. Just don't use tick, and just walk away. And a junior developer will have this advice, and don't use tick, never, ever. Is it a forbidden function? By the way. I got Victor from DevTeam Live to draw these comics for me. If you like these comics, you should go to his website, devteamlive.com. He also has this book, the painfully relatable book about game dev. It's amazing. You should check it out. Thank you, Victor, for joining my presentation. But yes, the issue with tick. People say tick slows down your game, but it's actually doing a bunch of work per frame per actor that is slow. It doesn't really matter whether you're using tick or timelines or timers, or if you decided to have an animation with an anim notify every frame because I'm not using tick anymore. The overhead isn't usually the issue, it's all the work that you're doing. And if you need something to happen every frame, just use tick. If you need something to happen every frame, and you're like, I'm not going to use tick because I've been told not to use tick, so I'm going to use a timer or a sequence instead, or timelines, I mean, then you're kind of missing the point of why this advice is being given in the first place. It's not the tick is evil function. They're just trying to get you to not do so much work every frame. For Fortnite, for example, we actually have a bunch of ticks. In the Fortnite client, which runs, by the way, on Android and Switch, we have about 80 ticks on average for a single session. So in the beginning, there's of course way more because there's more players alive, and in the end, there's way fewer. But on average, about 80 ticks per frame. And on the server, we have about 700. But try not to do too much work each frame, no matter which method you use, even if you're not using tick. And that can be from either having just fewer ticking actors or doing less work per tick. That should be the advice. And also just don't tick actors that have no business ticking. For example, let's say you have a bullet hell game and you have 1,000 bullets, and these should not each be their own actor with their own tick function, because then again, 3.5 milliseconds of your frame time, which is a good percentage, would just be going to the tick overhead. In that case, you should aggregate ticking. There's actually a great presentation about aggregate ticking by the Sea of Thieves developer online. It was at Unreal Fest, the first Prague one before COVID. So in that case, just make one actor called like bullet manager and have the bullets be, for example, instant static meshes. Then you only have one tick, but you're doing a lot of stuff. And if you do have a lot of data you need to crunch, you can use mass. I'm not recommending this lightly. Mass is like a very involved system. It needs like a programmer, but you have that option. And I was talking to the Unreal Source Discord channel. Discord admins say, woo! They're here. Yeah. So unrealsource.com. Go there. There's like 111,000 members there. Anyways, I was talking to them about this presentation, and Chaos Spectrum said, you know what? I think you don't use ticks is a bad advice. I think the advice should be use ticks, don't abuse ticks. And I was like, oh, I'm stealing this, but I'm quoting him, so it's not real theft. But when do you know when you're abusing ticks? Well, you profile. Just profile, tick the profiler. Everyone has access to it. So yeah, when it comes to don't use ticks, I would say this is a bust. You can use ticks. However, don't do too much work in ticks, and of course, don't have an unreasonable amount of ticks running. And when do you know when you have an unreasonable amount of ticks? You profile. You profile, okay. Next myth. You cannot make 2D games in Unreal. Who says this is true? You cannot make 2D games in Unreal. I see 1, 2, same amount of dimensions as there are people that say you cannot make 2D games in Unreal. But for prosperity, how many say this is bust? You can definitely make 2D games in Unreal. Okay, no one's going to be called the coward this time. Actually, you know what? I don't know. I've never made a 2D game in Unreal. But it's okay. As a scientist, I asked someone who does. I found someone online who actually is a torchbearer for 2D making games and tutorials. His name is Cobra Code. Cobra Code, can you please answer this myth for me?
Hello everybody at Unreal Fest, and
Where's
thanks
my
for
sound?
having me as a guest, Ari. I'm Cobra Code, and I've dedicated the last 3 years of my life to teaching people how to make 2D and 2D/3D hybrid games with Unreal Engine. Like most other developers, I also thought making 2D games with Unreal was impossible, or at least unfeasible. Since a few years ago...
Okay, let's do it again.
Hello everybody at Unreal
Hello.
Fest, and thanks for having me as a guest, Ari. I'm Cobra Code, and I've dedicated the last 3 years of my life to teaching people how to make 2D and 2D/3D hybrid games with Unreal Engine. Like most other developers, I also thought making 2D games with Unreal was impossible, or at least unfeasible. Since a few years ago, there really wasn't much information about it available. But after I decided to just give it a try, I quickly realized the untapped potential of Paper 2D. Paper 2D is an official plugin that has been around since Unreal Engine 4.3, allowing us to create sprites, flipbook animations, tile sets, and tile maps inside of the editor, and it's actually active by default in all Unreal Engine projects. These sprite assets can then be used to create 2D games that consist of sprites only or 2D 3D hybrids which mix 2D sprites with 3D elements. However, sadly Paper 2D hasn't been in active development for quite a while and some features are stuck in a perpetual beta state. Doing things such as triggering events on certain animation frames, multi-directional animations, and switching between animations in general all have to be done manually within Blueprints or C++, which works just fine but can often be cumbersome and time-consuming. This is where the free Paper ZD plugin steps in, which is an Epic Mega Grant recipient and extends Paper 2D's functionality. It allows us to create 2D animation blueprints which look very similar to the ones we get with skeletal meshes, enabling us to use state machines for switching animations, set up animation notifies to trigger events on flipbooks, and it even has built-in support for multi-directional animations with up to 16 directions, making it easy to create top-down games. Using these tools, the possibilities are almost endless, and I've made prototypes for jump-and runs, beat-em-ups, top-down adventure games, action platformers, and much more. You may be concerned about performance or the package size, but there are many ways to reduce package size with Unreal. And I've gotten 2D games down to an on-disk size of roughly 150 megabytes and a download size of roughly 90 megabytes. Regarding performance, I was able to make a blueprint-only 2D game run at 370 FPS on the Steam Deck by only changing a few project settings. There are also many more Unreal 2D and 2D 3D hybrid games than you might think. The Octopath Traveler series or Ender Lilies are the most well-known examples, but there are also many other awesome projects such as The Siege and the Sandfox, The Vagrant, Demon Crush, Snacko, Forgive Me Father, and Born of Bread. True or bust? In this case, it's a bust. You can make 2D games in Unreal just fine as long as you know how to work around some limitations and spend a bit of time on optimization.
Thank you, Cobra Code. And actually, since Cobra Code made this video for me, he's actually released the Ultimate 2D Top-Down Unreal Engine course, and I got his permission to give you this link, which has a huge discount on the course. Or just go to tinyurl.com/Unreal2D-Top-Down. Few more seconds so you can take a picture of it or something. Okay, thank you for busting this myth. Next myth is blueprints are slower than C++. What even are blueprints? Well, blueprints are Unreal Engine's visual scripting language. It looks like this. It's got nodes, so you don't have to be coding. You can just do some visual magic things. Okay, anyways, people say blueprints are slower than C++. Who says this is true? They are slower. Okay. So about everyone. Who says this is a bust? Blueprints aren't slower than C++. I'm a designer. One designer there. 1, 2, 3, 4, 5, 6, 7. About 7 out of 300. Thank you. Let's talk about blueprints. So blueprints do run in a virtual machine, and there is a set overhead for each blueprint call. But after that, it is all in C++. That means if you have very few calls, you have negligible overhead. And I made a little function here. Just an example. And so it prints a string, it does some work for the amount of time that I tell it to do some work, and then it prints a string saying it's done. And calling into a C++ function like that, that's been marked with a U function, you can call into it, it has about 0.8 microseconds of overhead in the editor before it gets into it on my computer on 5.4. And then in a package development game, it takes 0.7 microseconds. But that's not the only overhead. There's also an overhead between the nodes. So in the editor, in Blueprints, it will take about half a microsecond. And then in a package development build, it will take 0.1 microsecond, quite fast. And yeah, how much slower is it? Well, let's check out a few different amounts of work. Let's say doWork is doing 1 millisecond of work. This is a screenshot from Unreal Insights. It's the time. It goes from left to right. And then when it goes into a function, it goes down. First, we have print string. Then we have doWork, 1 millisecond. Then I have another print string, which in this case is taking 272 microseconds. And blueprint overhead will show on the profiler as a space between the functions. And when you go into C++ land, it will show as offset. And there's not really anything there. So this function, in this case, is about 0.00001% slower in that case. But OK, doWork 1 millisecond. 1 millisecond is a very heavy function. That's like 4 character movement components. So let's divide it work by 10. Let's make it take about as long as the print string is taking. So here we have print string taking 90 microseconds in this case. I don't know why it jumps between 90 and almost 300, but maybe it's flossing or something like that. Anyways, print string 90, then do work 100, and then print string 95. Now you can actually see, if you squint, 1 pixel between the first print string and do work. And if you squint really hard, you might see 1 pixel, maybe 2 offset between do work and do work C++. But OK, let's say, well, 100 microseconds is still quite slow for a C++ function. Let's go to something a bit more realistic. So anything between 10 and 100 microseconds. Let's go to 10. Now we can start seeing the overhead. Now we can see the space between the functions, and now we can see the offset. The offset between do work and do work C++, you can see 10.8 versus 10. So that's the 0.8 microsecond overhead that I told you about in the previous slide. But let's say I want to see it with even faster function, a C++ function that does just almost nothing. It's one microsecond of work. In this case, the overhead is actually between the nodes and the offset is a bit more than what the C++ function is doing. And this is when you're calling into C++. There are also other nodes, for example, there's math nodes, set, for each, that are only in blueprint land, and those are basically 100% overhead because it never goes into C++ land. So why am I showing you all of these different numbers? The thing is, like, how much slower are blueprints? Are blueprints is usually a question, and it's not really a multiplier. Like, it's not like, blueprints are 10 times slower than C++. Although, like, we have set that, but we're always given the context of, like, but it depends. So sure, for some graphs, like if you have lots and lots of nodes doing a healthy mixture of like math and stuff, it might turn out that one specific blueprint's 10 times slower. But usually you should think of it as an overhead per node. That's the overhead. And when it comes to just best practices for blueprints, I actually decided, Michael Alar, I decided to get his input on it because he's been giving advice to Unreal developers online for like so many years, and I was like, Alar, you're so smart. Can you help me collaborate on this? And he's like, I got you, fam. And he sent me this video, which I just put in right now. Let's check it out. Let's check it out together.
Should I use blueprints or
Shut
C++?
up.
Use whatever's comfortable. But I heard blueprints are slower than
Use
C++.
the profiler.
Oh, that's it. I thought it would be longer. The other one was like 3 minutes. Okay, thank you, Michael. I actually agree with it. This is quite nice. But I'll add a few more best practices of my own. If the blueprint overhead for some code is causing you issues, you should move that code to C++. Because, believe it or not, there is no trophy for shipping a game in blueprint only. I know some of you might be purists, like, I don't want to touch C++. But the thing is, like, if you go to the Game Awards, you don't see Jeff Keighley on stage saying, and for the game that made a game in only blueprints. There's nothing like that. There is an award for the best game. You should try to get that, the best game. And if that means moving a couple of your functions to C++ only, even though you don't get to call yourself a purist anymore, if it helps you with the game, you should do it. But that only gets you so far. Let's say you take a function and you see on the profiler, oh, it's so slow. Let's move it over to C++. But oftentimes you're just still doing too much. It's still slow. Like, sure, moving it over gave you like a 20% speed up, but you can't, for the same function, like just do it again. I mean, I guess you could move it over to assembly. Don't do that. Don't do assembly. Sorry, forget I said that. Because oftentimes you're just doing too much. Then you might decide, oh, I know, like all the enemies, they're taking too much frame time. I'll only have the enemies that are close to the player take every frame. And the enemies that are a little bit further away, I'll take them every other frame. And the enemies that are behind the player, I'll take them once a second. And think about, like, those are good optimizations. But the thing is, those optimizations would have been valid whether you're using blueprints or C++. So yeah, like moving things from blueprint to C++ isn't a Hail Mary. It's not going to make everything like super fast and just run wonderfully every time. Sometimes just doing less per frame by being smart is the way to go. And how do you know whether you're simply doing too much? You profile. You're getting it. Okay, so when it comes to blueprints are slower than C++, it wasn't a trick question. It is true. But that doesn't mean you shouldn't use them. Not at all. They're also super versatile and very fast to iterate on. And they enable non-coders on the team to contribute code, which is very nice. You know what? I did some tests. I ran some numbers. I actually figured out the best mixture, the best ratio of blueprints versus C++ to have in a project. There's a single answer to it. And the answer is, whatever ships your game. that's it. If you are a bunch of designers and you don't know how to code and you want to make a blueprint-only game and ship it and make lots of money to make your next game, that was the correct version, the correct ratio of blueprints versus C++. If you're a bunch of hardcore coders and you hate blueprints with the passion of 1,000 suns, then do it all in code and ship your game and make enough money that you can make your next game. So yeah, that's the perfect ratio. I actually asked one engineer, how much blueprints are there in Fortnite? And they quoted, I don't know if they allowed me to quote them, so this will be an anonymous quote. They said, a lot all in caps. So in Fortnite, we have a lot of blueprints. Next myth, don't use cast. Ooh, spicy. What is cast? Cast is a node that converts a pointer of some data type to another type with type checking. For example, just to give you an example of what it means, like here we have, let's say it's a trap, and we have a begin actor overlap. Whenever something overlaps with a trap, I'm going to say, is this actor, which I don't know anything about, is it the player character? Because if it is the player character, then I can get the reference to the player character. Now I can call functions on the player character. You basically cast to it. But some people say, you shouldn't use it. Don't use the cast function. Who agrees with this? Who says you should not use cast? Let me see the hands. 4, 5, 6 hands out of 300. Okay. Who says this is bust? Oh, you can definitely use cast. Okay, about 80% of you. The rest of you are cowards. Let's talk about cast though. Some say cast is slow, cast loads assets as a reason to not use cast. But the thing is, the cast function is an integral part of coding in both blueprints and C++. And it's not this slow. It's about half a microsecond in C++, and it's about 3.5 microseconds in Blueprint Editor, which is about the same as the tick overhead, because it's just the blueprint overhead, basically. But this is on my computer, so your mileage may vary. But the issue with cast is that casting to a blueprint type will also reference it, which adds it as a dependency. And dependencies, they need to be loaded before your blueprint is loaded. And they stay loaded while something references them. Give you an example of where this was bad from an actual real-world example. You have a player character, and they have a function called I've been grabbed. And we had this last boss of the game that would do something special when it grabs you. So we would, of course, cast to the last boss and say, if it's the last boss, do something weird. And I'll tell you, like, you can have all the systems in the world for all the enemies, that just always works. But when it comes to your bosses, you're going to need to do some weird stuff all around your game. And like, that's just the way, like, it's just like bosses they are really cool and they do a lot of cool stuff. And you're just going to have to deal with it. But the thing is, now because of that reference, before the player can be fully loaded, it first also needs to load the end game boss. And while the player is loaded, which is always, the player boss was in memory. So that means that, yeah, the game loaded a little slower because it needed to load the end boss before the player could be loaded. And it also meant that we have memory pressure, like the end boss always, and its meshes and everything in memory all the time. But the thing is, it doesn't slow down the actual cast operation itself. That's always just as fast once you've loaded it. So, okay, when should we then cast the blueprints? I made a flow graph. Who doesn't love a flow graph? And let's say we have an actor reference, and you want to do something with it. What do you want to do with it? Do you want to call a function array, or do you want to get a property from it? If yes, I have another question for you. Is the function or property declared already in C++? Because if it is, let's say in one of the parent classes, because if it is, you can just cast to the C++ parent class, because the C++ classes, they don't count as asses. They're always in memory, and they're quite tiny. So you can cast to them without any penalty of reference loading. So just do that. Feel free. That's fine. You have my permission. But what if the function or property is not declared in C++? I have a new question for you. Is the blueprint class expected to be always loaded anyways? Let's say, is it the player character? Is it the game instance? Is it the game mode? One of these classes that you know is going to be in memory at that time. In that case, just cast to that blueprint. Because even though you're adding a dependency, if it's already loaded, Unreal isn't going to load it again. It's smart enough. It'll just go like, I need to load this. Oh, it's already loaded. Never mind. So just cast to the blueprint, cast to the player character, cast to the game instance, go ahead. But what if the blueprint class is not expected to be always loaded? I would say, then get a programmer, or yourself if you're a programmer, to define the property or function in C++, and then you can override it in Blueprint And that way, you can cast, again, to character. But what if you don't want to call a function on it? What if you, no, sorry. What if you don't want to define a property or function in C++? You're going for that purist Game Award trophy, which doesn't exist. Or maybe you're like, there's all these different actors and they have different parent classes. Or it's like, I can't or I won't. In that case, use an interface. That's what they're for. Many people will default first to going for interfaces. I would say first cast to the C++, because that's just like, in my opinion, way better. But if that can't or you won't do it, then use an interface. Go ahead. It's totally fine. But now, if you don't want to get a function or a property from the actor, what if you just need to check the type? I would say, don't use the cast function. You should use this function. Compare it with soft class. You use isA of the type soft. So the object goes in, and you say, is this a soft class player character? And when you do that, you're not adding a reference because it's soft and not a hard reference. And some of you might be thinking, I've never seen that function before. Well, OK. You got me. It doesn't exist. We added it in 5.5. It's going to exist very soon. But until 5.5, it's fine. You can make this functionality yourself. It's actually quite simple. Just get the player class and resolve it. Casts it to a class if the class is loaded. And then get the actor class and just compare them. And if it's not, and if it isn't loaded, the player class will resolve to no, which in that case, it's not the same thing because it's not loaded. OK. And also, you can, of course, use actor tags or gameplay tags. Just check, like, oh, does it have a jumper on it? Then probably it has the jump function, something like that. And yeah. But if you don't need to check the type, and you still want to use cast, I don't know what you're doing, but you probably don't need a cast. But yeah, when it comes to don't use cast, I would say this is a bust. You can use cast all you want. Also, if you're doing this in C++, it doesn't really apply there. If you're a C++ programmer, you're already using cast left and right, and you never heard this rumor probably. But yeah, be careful with hard references. That's the only thing. Next myth. If it can be Nanite, it should be Nanite. Ooh. Actually, I have no idea. I'm not a tech artist. And the guy who said it, Matt Osterley, he got people questioning this one. So I just went to him. I said, Matt, you need to answer this one. You started this. And yeah, Matt Osterley is not, unfortunately, Matt, we miss you. But he is here virtually. So he is going to take over this myth for me. Matt, take it away.
Thanks, Ari. That's right. Some of you may have heard that if it can be Nanite and you're using Nanite, it should be Nanite. But that seems pretty flimsy. The myth I want to bust is everything should be Nanite because it will fix everything and run faster always. And I think it's helpful to have a basic understanding of what Nanite is doing before we start raising hands. Put quickly, Nanite is a virtualized micropolygon rendering system that aims to performantly provide nearly pixel-perfect LODs at a higher level of fidelity than was previously possible than with the traditional lotting and rendering techniques. It does this by first grouping your input meshes into clusters of about 128 triangles, then simplifies that geometry into lower and lower levels of detail. These clusters are streamed in as needed to achieve a resolution of no greater than 1 pixel per edge. Prior to rasterizing, Nanite culls primitives, instances, and even individual clusters in order to ensure it only rasterizes what's visible. Then it chooses a rasterization method based on the size of the triangles in a cluster. Bigger triangles use the traditional hardware rasterization path, whereas more dense clusters use Nanite's software rasterization path to efficiently rasterize those small triangles. Rasterization sends the pixels occupied by each material to the base pass for shading. So 3 different rocks using the same material all go into a single shading bin. And Nanite's new compute shading means it only needs as many shading bins as there are materials visible on the screen at any given time. Pretty great, right? So what do we think? Do we think this myth is true?
You kind of changed the question, but I'll allow it. So everything should be Nanite because it will fix everything and run fast always. Who says yes? 1, 2, 3, 4, 5, 6, 7. I like how the hands just keep popping up. 7. Okay, Matt, it's 7.
Or do we think it's bust?
How many think this is a bust? The rest of us. Matt. Almost everyone thinks this is a bust. Do you think that's fantastic?
Fantastic. Let's break this up into 2 parts. First, what if I told you not everything can be Nanite? Translucency and Niagara aren't supported, and skeletal meshes are experimental just now in 5.5. Additionally, Nanite isn't available on all platforms, so if you're targeting those platforms, you'll still need to plan for non-Nanite paths. But surely the things that can be nanite will improve performance, right? Actually, it's quite possible to cause new and different performance issues than you're used to from non-nanite rendering. Stacking geometry closely together means that nanite can't effectively cull the clusters of the further mesh, which could result in bottlenecks due to nanite overdraw. Expensive masked and WPO materials can result in significant programmable rasterization costs for nanite and VSM by extension. You can also cause rasterization issues if your WPO material scales a cluster in such a way that its transformed size mismatches its untransformed size, and thus the cluster's raster mode is mismatched. And you can create an excessive number of shading bins using things like dynamic material instances. So what does this mean for our myth? Well, not everything can be nanite, and nanite can cause its own performance problems, which means I think this is a bust. But I don't think that means you shouldn't use nanite. Leaving aside the performance benefits of nanite to the other rendering systems like Lumen and Virtual Shadow Maps, nanite does allow for models with a higher level of detail than previously feasible through its new approach to simplification and rasterization, and it can prove more efficient when rendering scenes through its bin shading approach. Just remember to profile, evaluate, and optimize as you go. Back to you, Ari.
Thank you, Matt. Look at that cheeky bugger. Okay, I actually think he reworded the myth just so that he could say that he came on my presentation to bust himself. Dirty boy. Okay, next myth. Thank you, Matt. Get all actors of class is slow. What is get all actors of class? It's a function that allows you to get a list of all actors of a certain type currently alive in the world. And depending on who you ask, some people will tell you you shouldn't use it because it is slow. How many people say this is true? About a quarter to a third of us think this is true. How many of us think this is bust? You can use that function. A third of us. Cowards. This is a divisive one, but don't worry. I'll get into it. Let's talk about get all actors of class. The thing is, it scales directly with the amount of actors it actually gets. So if you're only getting few actors, a few dozen, it's very fast. And honestly, it's used by the engine. We even call it a few times every frame in shipping builds. There's 3 calls to it by 2 of our subsystems. And some of you might be surprised. And I think maybe some of our rendering engineers or like engine engineers might be like, oh, really? And I might look into it. Anyways, yeah, it's happening. And it's not noticeable because it's very fast, right? It actually uses hash buckets, so it's very efficient. It used to loop over every single actor in the map and check if the actor was of the type. So it used to be slow. It used to be true. But you know what? I decided to check just how long ago was that. It has not done that in over a decade. This myth has persisted. I checked. It's 11 years ago that we changed that. But I will say one thing. We did forget to change the comment for the note. The note says, this is very fast. No, very slow, I mean. Don't use it every frame. Sorry about that. That might have caused a little bit of misunderstanding. My bad. But during this presentation, we noticed it, and we decided to fix it. So in 5.5, this comment has been fixed. Yeah. Woo! So no more misunderstandings. Yeah, thank you, Ben Ziegler, for changing those comments for me. Of course, that just means don't get an unreasonable amount of actors, and don't do too much work for each actor if you're looping through it. Again, just like, don't do too much of anything. However, its siblings, we have get all actors with interface, we have get all actors with tag. They still don't have any hash buckets. They loop over every actor, which is slow if your world gets big. And the bigger your world gets, the slower they get. So that means get all actors of class. It's always fast no matter how big your world is, as long as you're only getting a few actors, like a few dozen, maybe up to 100. But after that, like, it does still do a check on every actor. Is it alive? Is it pending like incremental garbage collection? So if you go up in the thousands, you're going to see it. But how do you know how many actors are too many? You profile. You're getting better at that. So, okay, get all actors of class is slow. Is that true or bust? I would say this is a bust, but for a reasonable amount of actors. And of course, if you're looping through them, make sure that you are mindful of how much work you do for each actor. Next myth. Don't use child actor component. What is the child actor component? So it's a component that allows you to have your actor automatically spawn and attach a child actor during construction. And for some reason, a lot of people say that you just should not use it. How many people agree with that? How many people say you should not use the child actor component? Only like 10, 15% of us? Okay. How many people say this is bust? You can use the child actor component. Go ahead. About 20 to 25% of us. Okay, we're getting more into the weeds now, which I like, but I don't like how many cowards there are in this room. Let's talk about the child actor component. Users coming from other engines will often use it to replicate prefab functionality. When they do that, they encounter issues, instability, and crashes. Because child actor component, it doesn't really stress test our re-instancing system. We do use it. We use it on Fortnite, but for very simple attachments, like only for visuals, for VFX, and we don't do any nesting. Anything more complicated, like if it's related to replication or nesting, you want the child actor within the child actor, or it'll probably give you issues. If you want to get close to a prefab workflow, you can just attach, like within the actor blueprint, the components to each other, so you can have like child components there. Not child actor components, just child components. Or you can, even in the world, you can attach pre-existing actors in the world outliner. That's not really a prefab workflow though. Or you can use level instances, which now in 5.5 or 5.4, I can't remember which one, will allow you to do per instance override. So it's like kind of diet prefab. But the thing is, we do have scene graph, which will have a way better prefab workflow. It's the prefab workflow that you know from other engines, not gonna name them, but the ones you kind of expect how it will work, right? And we actually have it right now experimental in UEFN. I don't think you can publish your islands yet with it, but this is a great time for you to finally check out UEFN. Just see how this works for you and if it fulfills all of your conditions, because if it doesn't, you should tell us now, because now we're like molding it. So if you just forever hold your silence, we will assume you love it. But yeah, don't use child actor component. It's true. Don't use it. I would say that because of all the issues. Maybe if you have very simple use cases, you only want to attach, a visual or like a VFX or something, no nesting, no replication, nothing like that. Sure, do it. That's how we use it. That's how kind of we meant to use it, but we didn't know users would just go like apeshit with it. So don't do anything more with it than that. So yeah, just like as a good rule of thumb, just don't use it. Okay, next myth. Unreal cooks everything by default. Cooks everything. Ari, what you cooking? So cooking, when packaging your game, Unreal needs to cook the game's assets to run on the target platform. This is like compressing textures, compiling blueprints, compiling shaders. And you would think that maybe it only cooks only what you use, or you would think that maybe it cooks everything by default. Who here says, yeah, that's true, it cooks everything by default in your project? 1, 2, 3, 4, 5, 6, 7, 8. I see half hands. Put your hand all the way up, don't be shy. Wow, 9, okay, 10. Okay, who says this is bust? It only does like what you actually use and stuff like that. Okay, about half of you, the rest of cowards, blah, blah, blah. Okay, let's talk about cooking. Cooking is time consuming, it's very time consuming. If you've seen some of the other talks, we're trying to make it faster. But in any way, you only want to cook the assets your project actually uses. But the thing is, Unreal cannot know which assets you're using or not. Like, for example, what if there's an actor that isn't referenced by anything, but you want to spawn it via code, just with its path? So if you don't tell Unreal which assets you want it to cook, Unreal will just default to just cook everything. So that's the default. So like, you can break that functionality by just telling Unreal to cook anything, and then we'll just cook that and nothing else. So how do we tell Unreal what we want to cook? There's a few ways of doing it, but I recommend that you use the primary asset rules. And you can configure them in the project setting. Just change the map rule to always cook and disable the editor only checkbox to only cook all the levels in the maps folder and only that folder. And then what they reference and what they reference and what they reference and so on. And of course, like your game instance, game mode, those will also get cooked, of course, because they're being referenced from the project settings. And I think this should be the default personally, but of course I understand, like what if users want to do something weird, like spawning something dynamically from code, then okay, let's just cook everything. But if you do that, it's gonna be closer to like what I expect Unreal to do by default. And if you need other classes, for example, you have like dynamically spawned enemies or collectibles that you only spawn via code and you want to be able to reference them, I would say make them primary assets. You do that by just overriding the get primary asset ID function and then listing them in the primary asset types to scan in the project settings. That's all you need to make something a primary asset, and you can give it a quick rule. Or you can override the asset manager, which I recommend every bigger studio do. It allows you to just basically go haywire on making like everything super customizable. But for smaller projects, don't bother if you don't need it. There are other methods, of course. You can put something into directors to always cook, or you can use the maps to cook. Yeah, that works. You can use both, either or. I recommend just going full on with the primary asset rules or customizing the asset manager. So when it comes to this, Unreal cooks everything by default. It's actually true, but it's easy to change, which you should do. Okay, we have one more myth. And that is, you should avoid redirectors or clean them up as soon as possible. What are redirectors? Glad you asked. They are small metafiles that Unreal leaves when you move assets. And this metafile then points to the new location of the asset. And this is needed because Unreal doesn't use global unique identifiers, GUIDs. It uses file paths. So if it's pointing to something and it moves, the asset, it's still pointing there. So the redirector will tell it, oh, look over there instead. Oh. Okay, but people say, the redirectors, don't keep them in a project. You need to avoid making them, or if you do make them, you should clean them up as soon as possible. How many people say this is true? Oh, wow, like 2/3, almost 4, I would say just almost everyone, like 80% of us. How many people say this is bust? 12 out of 300. Let's see, let's talk about redirectors. The thing is, if you're not connected to version control even, Unreal won't even create them in the first place if you can avoid it. It will just fix them up immediately. So if you move an asset, Unreal will go like, wait. And it will go to every asset that points to that asset and say, the asset is over there now, and then resave them. It's a little bit slow, but at least you don't have to worry about redirectors. But they are important in team workflows, however. And I'll give you one example of why you shouldn't fix up redirectors as soon as you can. Let's say Anna creates a new asset, which she has not committed yet, it's just on her computer, and that points to blueprint important. Like this. I practiced this and now I fuck it up. Okay, anyways. If Bill moves blueprint important, Unreal will leave a redirector in case any asset anywhere points to it. The thing is, Anna hasn't committed her asset yet, so Bill might remove that redirector thinking, he fixed up all assets that were referencing it because nothing was committed that does still. Now Anna commits her asset, and it breaks the project because it's referencing an asset which doesn't exist in the location anymore. So yeah, this is the reason. And you might think, this is very rare though. You're right, it's very rare in smaller projects. And as soon as your team starts scaling up, this rare becomes a bit less rare. And it becomes a problem that you have to fix every once in a while. Especially at a scale like Fortnite, this is such a big issue that we actually have a rule of when to fix up redirectors. For us, it's best to do it when you can be sure no asset, whether it's committed or not, is pointing to them. And how can we know that? Well, there's actually one time of year when everyone goes on a holiday where we just start a task that resaves all assets and fixes up the redirectors, and then we okay, turn off the lights and leave. Just after everyone leaves on holiday. And you can do that via the resave packages commandlet. We don't really have good documentation about it, sorry. But if you just search for resave packages commandlet, there's a C# file that basically calls the C++ commandlet. There's two classes called resave packages something. Check them out. It will show you all the parameters and stuff like that. Or maybe if some of you figure it out, maybe you can make an article on ETC. Tell me about it, and I'll link it from the text version of this article. Anyways, when it comes to avoiding redirectors, clean them up ASAP. Maybe for very, very small teams where you're not worried about it, but I would say this is a bust. You should only clean them up when you know no one else on your team might be referencing them. This was the last myth. We only have 30 seconds left, so I'm not going to take one question right now. But I will be at the Dev Hub right after this for a whole hour. You just follow me, and we'll go there right after this. But I will just hope you have a great rest of Unreal Fest Seattle, and I want to say thank you very much.
Hi. Hello, Seattle. Hey. So I am Arvind Neelakantan. I am here to talk about Unreal for mobile. I see a lot of enthusiastic hellos, which is great. So there's a lot of folks working on mobile-based Unreal Engine project or interested in Unreal Engine for mobile, which is excellent. Good times. A quick run through of the agenda today. I will be doing what is Unreal for mobile introduction. I'll also talk about Android-specific workflows. And I'm talking about Android-specific because there is a lot to cover. A lot of this will also, of course, translate to iOS. But I'm sticking to Android for now, which will include like editor setup. How do you use the old and the new mobile preview? How do you do chunking, the new Android game development extension? And then how do you also increase your C++ iteration times? I'll also talk about mobile optimization, or rather mobile-specific optimization, which will run through how do you optimize your meshes, textures, talk about PSO, caching, gathering, pre-caching, console variables. And when you're working in a very large team, especially when you're working on open worlds, streamlining your development plays a big part. So I'll be talking about Horde, where I'll walk you through how to set up the CI/CD pipeline. How do you do device management, especially when you're doing testing, both automated and manual testing? And then, of course, the future of mobile. Everyone has the same question, which is Nanite and Lumen on mobile. When is that coming out? Well, I'll talk about that too. So that's pretty much what today's talk is all about. There might be a lot of things that you folks know. I think there's a lot of experts in here who are working on mobile. So if you might know a lot of these things, and I hope by the end of this talk you learn something new that you didn't previously know. And if you're completely new to mobile, I think you'll pick up some nice tips from this talk. So introduction, I'm Arvind Neelakantan. I am a solutions architect. I've been making games for the last 15 years. I typically run around in India, in the Middle East, and Africa, providing technical direction to mobile developers. I am from India. And I also lead instructor-led initiatives where anything that requires infrastructure for training, I also lead that initiative within Epic. Now, mobile is very important for Unreal Engine. I think it was also in the keynote, so it's clearly very, very important. And you're not alone when you're making AAA games using Unreal Engine on mobile. There's a lot of folks doing it. We have Tower of Fantasy, we have the Oregon Trail, we have Ni no Kuni, and of course Fortnite itself. And from my neck of the woods, I'm from India and from Asia, we have Raji and Final Fantasy VII, Blue Protocol, all using Unreal Engine for mobile development. Now, a couple of months ago, I was in Unreal Engine or UE Fest Prague, where I gave a talk on AAA gaming on mobile. And this really is kind of like a sequel to the talk. There is a little bit of overlap between that talk and this talk a bit. But if you're interested to know about how to do build size optimize or reduction and talk about like a little more performance optimization and debugging, going deeper into debugging Android projects, that would be a good talk to look at on YouTube. And this is like a part 2 of that talk. So let's look at Android-specific workflows, including editor setup, mobile preview, chunking, and ADGE, or AGDE. So if you are working on Android, there is a really helpful doc on the Epic developer community where you can go scan that or go to that link, and that's where you can set up your Android editor or Unreal editor for Android deployment. You usually get it in a few tries. And then you could scroll down, make sure that you have your Google Play services if you're using that, and then make sure that your SDK, NDKs are all set up correctly, and you're good to go. For this talk, I am using a variation of Crop Out on mobile. For folks who are unfamiliar with it, Crop Out on mobile is a cross-platform game available in the Epic Game Store, or Epic Marketplace, rather. And it works on PC, and it also works on mobile. And what you're seeing on the right-hand side is me running it on mobile. Now, what I did, because this is an open world topic, I took this project and put it in a massive open world. Just dropped all the assets in there and made it work in a 2 kilometer by 2 kilometer world. And you know what? I just tested it out after making sure the UI, all of it works, and it just works on Android. I didn't have to do anything massively different. In fact, I was just if you look at the FPS, it runs at a good 60 frames per second, no problem, just like that. I didn't have to do any massive changes. And this is all thanks to a lot of improvements that's been done behind the scenes in the engine, which helps with this kind of massive world development in mobile. So one of the first things that happens behind the scenes when you're working on a massive world is the landscape GPU culling. Now, all the landscape tiles that you're seeing are just very compact instances, and they can very easily be culled on the GPU. And we do culling only for lot 0, because that's the closest to the camera. And it's very fast and very efficient. There's no support for shadow views yet, and the cool thing is it's enabled on all platforms beginning with UE 5.4. It is deactivated if you're using Landscape Nanite or Lumen, which anyway, most of the phones don't support Nanite and Lumen, so for mobile, we are actually pretty good. And if you're looking at the cryptic photo or the picture on the side, like what exactly does that mean? On the top side is my phone. I was running a, this screenshot is from GPU culling turned off in the first screenshot. And you can see that rectangle is my phone. And you can see a lot of the landscape were rendered. But if I turn on GPU culling, the landscape GPU culling, you'll notice that like a bunch of landscape tiles just disappeared in the view where I'm not looking at it. And this just works. With landscape GPU culling, massive open worlds on mobile works. Now, if you're curious how I went about setting up this world, it's quite easy. Just went up, created a new open world system, open world level rather. It's by default a 2 kilometer by 2 kilometer world. And I just populated the world with a bunch of assets. Now, you could do this with PCG, the procedural content generation tool, or you could use like editor utility widgets. I'm a programmer, so I just went in and wrote like a quick Python script, and it just goes about just dropping a whole bunch of static meshes. And I just ran that Python script, and it just places all the buildings from a particular folder and just drops them all in the world. I repeated the same thing for props and also for some animations. Created a landscape mesh added a landscape material to the landscape mesh, which is the default material provided by the Cropout project itself, and that's it. And then a few tweaks here and there to add the UI to make sure that it works on, the same game works on mobile as it does for the non-open world project. All of that was done, and this is pretty much all I did. Now, the first thing that you would want to do when you create an Android or iOS project is to preview that game on Android. Now, you'll notice that there is a little button on the top, which has the Android icon on it. And that is the one that will then recompile the shaders to show that on Android, to preview it on what that will look on Android. Now, if you don't see that button, because you need to then enable Android preview, you enable Android preview by going under Settings, and under Preview Platform, you have like Android OpenGL Mobile or Android Vulkan. By the way, on 5.5, this UI has very slightly changed, but it's in the same place. Once you do that, you'll notice that that icon shows up. Once you have this mobile preview or Android preview on your editor, the next thing you'd probably want to do is run it on your emulator. There is a mobile preview which is old, which has been around for a while, and you'll notice that a lot of shaders don't really show up in those in that emulators, and that's because it's an experimental, and it's an old way of working with it. You don't want to use this anymore, but I'll just show you how to use this anyway. So if you want to enable the old way of mobile previewing, you go under Editor Preferences, go under Experimental, and there is you have the Allow Vulkan Mobile Preview and Mobile PI with Preview Device Launch options. Once you have that turned on in your editor settings or editor preferences, you'll notice that there is a whole host of very, very, very old devices that will just show up, like S9, S8, S7, Pixel 2, which no one uses, but that exists. It still exists. And you don't want to use this anymore. So now we have a new and experimental currently mobile preview, which works in tandem with the Android provided emulator. So that can be turned on. You can see that there's crop out already installed on that. And you can see if I go under platforms, the emulator now shows up, and you can deploy it directly to the Android emulator, which is the preferred way of working. So how would you turn that on? It's quite easy. If you have the latest version of the Android Studio, you don't have to do anything. But if you have an older version, just go to the Android emulator archives, download any Android emulator that's greater than 35.2.7. Install that into your Android Studio. Make sure that you go to under your users and Android folder, create a new INI file called advancedfeatures.ini. You go about doing that. Fairly slow in typing, so I'm INI. Yes, I do want to change the extension. Yep, and then I will open that up in Visual Studio Code, and I need to add 2 lines to it. One is Vulkan turned on, and GL Direct Mem is on both those things. GL Direct Mem will enable hardware acceleration. Once you have those 2 in there, save your file, go back to your Unreal editor, and I want to have a caveat. This preview only works if you are running Vulkan builds. So if you have ARM64 or x86-64 builds, and with Vulkan, you're good to go and run the game on your emulator, Android emulator. You have that turned on. In your Android Studio, make sure that if you have an older version, just make sure that you have the right version of the emulator turned on by going to the SDK Manager, going under SDK Tools, and you can see that the emulator is running 35.2.7, which is the right version, and anything above that works too. Then just go create an emulator by going under Virtual Device Manager. Just create a device. Make sure that you have, and here all the latest and greatest versions of Android is available for you as OS. So I'm just creating like a Pixel 6 Pro, and Vanilla Ice Cream is the version that is the beginning version before the emulator is supported. So I'm setting Vanilla Ice Cream as the OS. Give it some name, and what's the default orientation. Finish it up, and that's it. Once you have that set up, just click on play, and now the emulator is turned on or will start. It'll just take a little bit of time. And once the emulator is on, it works exactly like your typical Android device, and this will be available as a device in which you could launch your Unreal Android game into. So once that's turned on, once it's turned on, just go into like platforms, as you would typically do if you have a device connected to your PC or a Mac, right? Just go there, and you'll see the emulator is there. Now you'll notice that there is a little warning triangle. That's a bug. That'll be fixed when we come out with 5.5 release version. But you just turn it on and have the emulator connect to your Unreal editor, and you just build the executable on that device. That's it. As simple as that. And this is a new version, and we'll keep chipping away on it. I'll talk more about it in a little bit of time. The next thing I want to talk about is when you're creating these large worlds, you need to have your asset or your game isn't going to be less than 2 gigabytes. It's probably going to be a lot bigger. If you go under Android, even if you have the large OBB files turned on, and even though there's like a 4 GB limit, and in fact 2 GB is what Google Play allows, but a 4 GB limit in general in the OBB file, your world might probably be bigger. Like Fortnite is much bigger than 4 GB, which is why you need chunking. For folks who are unfamiliar with chunking is kind of like your DLCs. You're able to download additional files after your initial install of the game itself. To enable chunking, just go under your project settings, go to your packaging, make sure that you use your pack file, that you have use pack file, and you are generating chunks. Chunks is where you're removing certain files or certain assets from being included in your build. Now you can check to see if the chunks exist or not by just going under the asset audit part of your editor, and you'll see that right now there are no chunks. And we'll come back to this asset audit in a little bit of time. Now, in order to create chunks, there are a couple of ways you can do it, but the way that kind of works all the time is going and creating a data asset, a primary asset label. And in the data asset, I'm just going to create that asset inside the directory where all of my static meshes or meshes that I want to include as part of my chunk is going to be. I'm going to create a chunk ID, which is greater than 0, and add cook rules about saying that it should always be cooked, include references, save that file. And now I did the same thing. This was under buildings. I did the same thing for all the meshes under the crops folder also. And now all I have to do is package the build. So I'm just going under Android. I'll package the build. And what will happen here is the buildings, all the assets under the buildings folder and all the assets under the crops folder will be separated out from the build. And now if I go back to the asset audit, and if I click refresh, add chunks, you'll notice that now there's 3 chunks there. There's chunk 0, which is the base game itself. And then there's chunk 101 and chunk 102, which is the name I had given. And you could go to the references and figure out, like, are they referencing the right assets? And they are. So you can see the chunk 101 is referencing all my static meshes in the building portion, and the chunk 102 will be referencing to all the crops. Now here is something that will be quite strange if you are developing for Android the first time, which is I created these chunks. I have the OBB file. Now OBB file is just an archive file, right? I can just open up the archive file. And in theory, I would have thought, like, hey, if I open up the OBB file, the chunk should be left out from the OBB file, because that was the entire point of this exercise. I want to not add to the size of the OBB. But now if I go inside the OBB file, you'll notice that all the chunks exist there, like this pack chunk 101, pack chunk 102, all sitting nicely and cozy in there. But we want to exclude it. So in order to exclude those chunk files, you have to do one more step. In your default engine.ini file, you got to add a OBB filter which says exclude these chunks when you're making the build. So I'm going to add a line which is called plus OBB filters, and I'm adding a wildcard which says anything that has the name star pack chunk 1 star, because my chunks are 101, 102. I'm going to add that, and then I got to make a build again. After I make a build again, if I go to my OBB file, open up the archive file, you'll notice that this now does not have the chunks. Like 101, 102 is all excluded from my OBB file. And now my OBB is significantly smaller. But it's not like these chunks got deleted. They do exist. So if you go under saved, staged builds folder, under where your Android file is, under crop out content packs, you'll notice that that's where all my chunks exist. And now the OBB file contains just chunk 0, which is the base chunk, which is required for your users or players to install the game, and any other things that's part of the initial build that's not excluded. And the rest of it you can download from, let's say, a CDN server, which you can learn how to do that by scanning that QR code. That talks about how to host the chunks on a server, and you can download them after the initial build is done. So there's also a QR code, and there's also the URL for folks who are watching it in live stream and don't have a phone handy with you. So that's how you have chunks done. All right, let's go to the next part, which is all about debugging your Android projects. How many of you have seen this happen, where you open up the game, and it just crashes? You open up the game, it crashes again. I don't know why the PowerPoint is not playing the video, but that's, believe me, that's crashing. It says cannot play media. I don't know why. Yeah. Well, I don't know how to debug PowerPoint, but I do know how to debug Android projects. So if you are facing crashes, I think the initial thought that you would go about when you're debugging it is like, I'm going to open up my logcat, I want to look at what the stack trace is all about, and do that, right? But there's an easier way if you're going to be developing a game using C++, and that's using the Android game development extension for Visual Studio. This is now enabled, has been around for, I think, a couple of minor version updates since UE 5.3, I think. And if you go through the Android projects, go to the developer site and download it, install it, and once you install it, in your project, in your Unreal project, just right-click that project. Oh, okay, none of the media is playing. Don't know what's going on. Maybe I need to re-present. Not like represent, but represent. Yeah, I think that should work. All right, let me swap that. All right, let's try that again. Go back. See, that crashes. See, that crashes. I told you it'll crash. Yeah, yeah. So it crashed. So to debug PowerPoint, just restart it. But to debug Android projects, you can extend the Android game development extension for Visual Studio. Install that, and then go and then generate the Visual Studio projects for your project. So right-click, generate Visual Studio project files, and you're good to go. Now, once you generate the files, go to your Android and package the project, because Visual Studio cannot package the APK file for you. It's only Unreal Engine which can do it for you. Once you do that, in Visual Studio, make sure you have either debug game or development game set up for Android, and set the target to be the target game that you're debugging. And you'll notice that I have my phone connected, like that's the SM-S911 is my Samsung phone. I have it connected to my device. I click on play, and this will then automatically launch the game on my device, and I'll know why it's crashing. Let's see that in action. Now, sometimes you might face this problem. If you're running Android 14, especially the older version of Android 14, it's fixed on the later versions of Android 14, you might get this SIGBUS error, which can be fixed by going to your debug properties. Under debugging, there is a LLDB post-attach commands. Again, this is fixed, and then add this thing there. If you're looking at like what that thing is, that's the thing. You add that thing there and that line there, and you should be good. You won't get that error. And that only happens on Android 14 for older versions. If you update to the later version of Android 14, you're all right. But this is what the experience will look like. You have I clicked on play, and on the left-hand side, you can see that's my game. It's connecting to my debugger. It's attaching to the process. It'll take a little bit of time. And if there is a crash, it should just find that crash. Let's hope that crashes this time. Let's see, crash. That crashed then. And now you'll notice that the crash suspiciously is in a class called crash actor. But it crashed and it was able to find the line in which it was crashing, which is super helpful. And using the Android game development extension, you can also add breakpoints if you're running a C++ project, and so it's super helpful. I'm a programmer, as you saw. I like using Python scripts, but this is super helpful. Like I can just go in there. I don't know who wrote abort there, crazy fellow, but that's what happens, and that's super helpful. And talking about C++ projects, you don't want to keep packaging the project over and over again if you're just making changes to the code. Now, there's a useful little utility in the editor. If you go under your project settings, under Android settings, there is a useful checkbox. They're called Don't Bundle Libraries into APK for Quicker Iteration, Experimental. So if you, and you can also, if you're like cool and you're like, I want to go to default engine.ini and write it myself, you could do that too, which is what is the don't bundle libraries in APK. So if you set that as true, next time you're going to be packaging the build, it's going to exclude all the assets. It's only going to include your C++ classes, which believe me, it greatly improves your C++ iteration times. All right. Let's look at optimizations, which talks about meshes, textures, CVARs, PSO caching, which everyone is talking about. So on mobile, Nanite isn't supported. So that's one thing off our head. But if you have a mesh that's Nanite supported, it automatically goes back to the fallback mesh. And sometimes the fallback mesh might be quite heavy, and you don't want to use it in your mobile game. But it's a cross-platform game. You don't want to just reduce the static mesh complexity. So instead, what you can do is if you go to the mesh, and if you scroll under, and make sure that you have LODs turned on, and have LODs generated. And under LOD settings, I have 3 LODs in this particular mesh. And under minimum LOD, there is a plus button. If I click on the plus button, I can now set specific overrides for mobile. And I can say, like, for mobile alone, when I'm packaging this game, only use LOD2. But for the other platforms, other platforms just use LOD 0 or Nanite, whatever works. But for mobile, use 2. And this means that first, your game will be a lot more performant on mobile, and also there'll be a significant reduction in your game size. And if you do it for one mesh, and I'm sure you have a lot of meshes in your game, you can copy that setting from that one mesh where you changed it, and select all other meshes, and you can paste the same LOD detail so that you don't have to do it for like thousands of meshes again and again. Just doing it once on one mesh will help you out. After you do mesh optimization, the next logical step is texture optimization. Now, texture optimization is also quite important because you don't want to have like 4K textures in your game. So this texture is a 2K texture, but I don't want this 2K texture in my game. I probably want to have it as a 1K texture. So if you have the texture open, it's important to set texture groups to all of your textures. And the reason why you have to set texture groups is once you have all of your texture with texture groups selected, you can go under platforms and device profiles. And the device profile is a super useful tool where it lists pretty much all the devices supported by Unreal Engine. And you can set overrides for each platform when you're packaging it for that particular platform. So you can notice that Android is over there. And you can also notice that there's a bunch of other Android platforms under it, right? But any changes I make on the parent Android profile will automatically propagate down to other Android devices also. So I go under the parent Android, I open that up, and I can now go under the texture LOD settings. And remember the texture groups, I can go under each texture group and say, like, when I'm packaging it for Android, reduce the 2K texture and clamp it to be a 1K texture. And you can do it for all other texture groups. Maybe for the hero character, you want it to be a 1K texture or a 2K texture, but maybe a boulder that's very far away, you can just kind of set it to like a 512 size. And while we are on the device profiles, the other thing that you could also do is add overrides using CVARs or console variables. In here, while again developing for Android devices, you can say like, I don't want to have grass turned on or wind turned on, or maybe you don't want to have physics in crop out. There's the little guys who are walking around have a hat that kind of bobs up and down that uses physics, but that's I don't care about it on mobile, but maybe it looks nice on PC. So I can turn that off just for Android using CVARs in the device profiles. Next up is shaders. When you're optimizing shaders, the first things I typically like to do is go to the platform stats button on the top and look at the performance, like the the instruction count on each of this shader. And if it's quite high, then you know it's quite high on mobile. But you'll notice that when you turn Android on in the settings, there is a warning that shows up which says it is, in fact, unable to extract the instruction count for that particular shader. And that's because Unreal Engine needs a Mali offline compiler in order to calculate the instruction count. So if you go under the editor settings and material editor, you'll notice that it's empty. So you need to go to the developer website, download the Mali offline compiler, and then point that Mali offline compiler exe file in the editor. And now if you go back, you'll notice that, hey, the warning is gone, and I can see the instruction count. That's pretty helpful. And finally, you don't want to keep writing new shaders for every platform that you're going to be targeting. And that's why we use feature level switch. And this has been around since Unreal 4.26 and above. And it's something that we use quite often in Fortnite, where you can just say, if I'm going to be having a shader that's only going to be, say, working on ES3 devices, and I can pass in a node which will only get compiled when I'm compiling for a ES3 device. But if I'm writing the same shader for SM6, you can have it rerouted to a different set of shader nodes, which is quite useful. Now, I wanted to get a screenshot of me doing this in crop out, but crop out was very efficient. So I kind of stole this from my colleague. And this is where on the left-hand side, you have a performance graph that shows like basic performance, like frame time, game, and render thread time. And once you move your camera and new objects get into your screen, you can experience a very bad frame drop and hitches. And I think most developers who have worked on AAA games must have faced this problem. And it has many names, but because we ran insights, we know that this was caused due to a shader compilation hitch. The modern name for this is PSO, or Pipeline State Object. And this is a PSO hitch that's happening because it's a bunch of shaders that was getting compiled while my game was running. Now, this is kind of fixed. It's like, hey, it's fixed. We don't need to do anything. Because with 5.4 and above, we already have PSO pre-caching turned on. Now, this is available with 5.4, but in 5.4, it only works on Android OpenGL. But if you have an Android Vulkan project on 5.4, you can just go to Android engine.ini file and just turn that on manually by putting in that console variable, which is r.pso pre-caching, and set that to 1. On iOS with 5.5, it's automatically enabled. And in 5.4, it did not work if you were working on a pre-computed lighting, but with 5.5, that's also fixed. And with 5.5, it's just enabled by default on all 5.5, or with 5.5, it's enabled on all mobile platforms, rather. But a little bit of history, right? Because this was just so easy. And I don't know how many of you have done PSO gathering before. But this is the current system that exists before we enable pre-caching. And that's, if you had that problem where shaders did not compile inside your game, what you had to do earlier was you had a developer or a tester run through the game through all possible levels and gather the PSO logs. And once you have the PSO logs captured, when you are running the game or when you're loading the game for your players, the PSO logs will be loaded and the shaders will be compiled when you're seeing that loading bar, and you'll note, and in Fortnite it will be called like optimizing game. I don't know how many of you have seen that. That's essentially just doing caching or running the PSO caches. It's just like generating those shaders for you. And this is not ideal because it obviously has very long load times, and it's also not efficient for your developers or testers to run through every part of the game. And especially if you have an open world, that's a fairly big task. Which is why PSO caching is awesome, because it just works automatically. There's no manual steps. So when a game loads, it just looks at every static, every skeletal mesh, all the materials. It looks at the landscapes and other components and starts queuing them and figures out like what are all the shaders that the user will potentially be seeing inside the game. And about a few frames before the player sees that particular object or particular mesh, the cache for that particular mesh gets compiled. And again, in crop-out, it works really well. So I had to like take a screenshot of this working on that sample project I was showing. And the PSO gets compiled on task threads. And there are some fallback strategies that you can enable in case the shaders aren't compiled. The first strategy is you can just tell the mesh itself not to get rendered. So the mesh itself will be hidden. Or you can have a default material, which is like a fairly simple material that will first show up on that mesh before the original shader is slapped on top of it. Now, both these default the fallback strategies are turned off. So you got to turn it on. And if you don't have it, turn it on. And for some reason the shader doesn't compile, you will still see that hitch happening. Before I head back to Horde, I do want to say like you could use a balance of both PSO gathering and PSO pre-caching in your game. So if you know that they're like at the beginning of the level, you know the players are going to be there, and you don't mind that initial loading time, you could still continue using PSO gathering and PSO caching. But PSO pre-caching is turned on by default anyway. You don't need to do anything, but that'll take care of other places where your developers, testers haven't been to. All right, Horde. When you're working on open worlds, you're working with a very large team. And in order to work with very large teams, you don't have to have, I used to be that one guy who was making builds all day on my PC and not developing anything and just sitting through the night, actually writing code. And to avoid that, we have Horde. Now, Horde is a CI/CD pipeline or a CI/CD engine, which is one of the things that it does. It also has mobile device management, which allows for automated testing and manual testing. Now, I don't want to go too deep into how to set up Horde, because you could go to that QR code or to that link, and there is a lot of documentation on how to set up Horde. But there are three things which really caught my eye, which is remote execution, where you have the ability to compute work on other machines if you have like a PC just lying around. So if you have like a C++ compilation, using the Unreal Build Accelerator tool, you're able to just offload that work to that machine. You also have a build automation, which is CI/CD. And finally, you also have the mobile device management on Horde, which is what is very interesting for me. Now, once you have this all set up, the way the mobile device management works is like you can have a pool of devices that you can use for testing, which is connected to your team. And you can check out these devices because they will have the APK files or the IPA files ready for you when the build is done. I do want to note one thing, which is Unreal Engine, the Horde only works if you're compiling from Unreal Engine source code. It doesn't work if you're using the launcher build of Unreal Engine. So if you're using the source code, Horde really works well. So you have the APK file, but how does it even work? So if you go under server, if you go under devices, you can see all of those devices, and the pool over there is the remote UE5. So you might have testers in another part of the world, and you can add new devices in there. I'm just adding a dummy device, adding where the device is going to live. It's going to be in remote UE5. I add the IP address of that particular device. I click on save, and now that device is available for testers. And the way that will be available is if I package a new build. I go under packages, I set it up as an Android build, and I have the device manager URL, which is the IP of where my devices are going to exist. And what is the device pool, which, if you remember, it's under remote UE5. I just start the job. And once the job starts, it will compile the editor. It will compile the game. It will automatically deploy all the APKs to all the devices that you have set up, which is fantastic. And you could then do testing. You could let your testers do the testing. And if you have automated testing, it will also run the automated tests on those pool of devices that you have. Now, this is not magic. This is just using build graph behind the scenes. So if you want to, and this is fairly well documented. So if you go to that link, you can use build graphs to create your own kind of jobs in Horde. Now, one of the jobs that I set up is creating HLODs. Now, when you're creating large worlds, HLODs is quite important. And notice that there is a tab called HLOD builds. That doesn't exist by default. I added it. Now, how do I add it? In order to create these HLODs manually, by the way, how many of you have created HLODs? It's a fun process, right? But I don't want to do it on my machine. So if I go under the documentation of HLODs, you'll notice there's a commandlet, and you just have to run that command in order to generate HLODs on your machine. And it's a fairly long process depending on how big your world is. So I'd like to just run that HLOD building on Horde. So in order to do that, there is automatically a JSON file. Like in this case, it's a stream.json file that gets created if you're installing, or if you have installed Horde. And in there, in the JSON file, I can add a tab. So I just scroll down. There's a tabs over there, and I added a title, which is HLOD builds, which is what you saw as a tab. And there's a template that I added called HLOD-build. And in the template, which is, again, if I scroll all the way down, I can define what this template needs to do. And that is defined using build graphs. So in here, keep scrolling down. You'll notice that that's the template. That's the HLOD build. And I have arguments in there where it's referencing a XML file, appropriately named Seattle build.xml file. And this XML file is a build graph. And I can also pass in parameters in there. So whether after the HLOD is built, do I need to commit that HLOD build into Perforce, and I can do all sort of stuff. So that's the XML file. So I can open up that XML file. I don't know how many of you can see that, but that's like a build graph right there on the top. a closer look, that's the build graph. And if you want to take a picture of it, you can. But that's the build graph, and it just says like run the same commandlet I showed you in the documentation page. It just runs the exact same command on this XML file, and I can pass in parameters and whatnot. And this is, by the way, the JSON file. If you want to take a picture or want to take a screenshot, you can do that. But now, if I go back to HLOT builds, that's a new tab I added. I can create a new job. I can then say like commit the HLOTs to Perforce after it's done building. I can click on start, and you can also set the build graph to say like build the HLOTs nightly or periodically or after every commit. You can do all sorts of stuff, and if you click on start job, it'll just automatically create the HLOTs. And this is a neat way for you to use Horde, because you can do a number of things. You can also have it run tests automatically. You could also have it generate chunks automatically whenever you're making a build, and everyone is happy, and you don't have to be the build master. So let's look into the future. Okay, I have 10 more minutes. Okay, the future, which is everyone's talking about Nanite and Lumen. So let's talk about that in a bit. So on mobile rendering front, like I said, we have PSO pre-caching will be enabled with 5.5 automatically. There's improvements with screen space reflection. Mobile forward support for all lit decals, rectangular lights, capsule, and point light with shadows will be enabled with 5.5. There is an experimental desktop deferred renderer with Lumen, which will be available only on high-end devices. There's again more improvements for decal improvements for Switch. There's also performance optimizations, and there's also the light HDR, which will then replace the existing LDR for mobile VR platforms. So if you're working on an Android like Quest-based VR device, I would wait for 5.5 before you begin development. And future, Nanite on mobile GPUs will be there. It's currently being supported on very high-end devices that we are testing internally, but we are working on it. And there's also improvements on the mobile forward renderer, again, for VR. At 5.5, and this is most probably my next talk in another event, which is all about memory insight support on iOS and Android, which will help diagnose specific platform issues or platform-specific issues which might occur. And this is going to be pretty awesome. Which will also, and there's also a lot of behind-the-scenes work that's being done in the editor, which will enable a lot of memory savings when you're deploying to iOS and Android. And you notice that I clicked a lot of buttons and added a lot of things on my INI files, and chunking had to be excluded in my OBB filters, and it's not ideal. So we are very aware of that. So in the next versions in the future, we are working on better discoverability of properties which are relevant to mobile platforms specifically. So you don't have to do a lot of these things. But that'll, and we're also working on better tools to analyze asset cost per platform. Mobile preview, I already gave you a preview of the preview. Which is how we have, but with 5.5, the mobile preview will be production ready. And there will also be on-device profile captures, which will just improve your on-device iterations for especially large games. Like the ones I just showed you, like C++ iteration is a lot faster, but even things like an easier deployment to mobile where you can even bypass the pack file creation and the slow copying that happens, all of that will be improved with 5.5 if you're developing on mobile. For the future of mobile preview, right now you saw the mobile emulator or the preview happening on one device. You can also now, in the future, have multiple simultaneous preview platforms running on Unreal Engine, so you can Unreal Engine builds, so that you can compare, you can run tests, you can run builds, and that's also being worked on. And there's also continued on-device iteration paths, and we also have an Unreal Remote, the Unreal Remote app, which is also being revamped on the future builds of Unreal Engine. And with that, that's it. Thank you so much. That's my talk. Thank you. All right, we have 5 minutes for any questions, but a heads up, I will be at the Dev Hub right after this talk. So if you have more questions, we can definitely follow up on those questions over there. But that's my talk, and I hope I see a lot of...
Okay, I think we're ready to start. We're going to be talking about Spice Frontier, a real-time frontier. My name is Sean Dunn. I'm the Chief Technology Officer of Steamroller Animation. I've been in the industry for many, many years, and I've been very lucky with the roles I've had. I've worked on the software side, I've worked on the production side, I've worked on the education side. So I've worked for companies like Alias Wavefront, when they were developing Maya back in the 90s. And then I've also worked for Epic Games, helping with Unreal Engine as linear content. And then I've also worked in production. I worked at Weta Digital, and I was fortunate enough to work on movies like Lord of the Rings and Hobbit and Avatar and slew of others. What I'll do is I'll give you a bit of an introduction of what Steamroller Animation is and what the company is. So we're a studio that we believe in flattening the boundaries and elevating artistry. We work really hard to do the best quality work that we can, and we've got a broadly talented team spread out among the actually all over the world, in fact. And this is a video of the company introducing it.
At Steamroller, we are super excited about the craft of animation. We love working with our incredible partners around the world, helping to support them with animation services as they bring their amazing projects to life. We also love creating our own original content. Our team is working hard on a number of new stories as we continue to build our animation pipeline, leveraging the power of the Unreal Engine. We want to thank our crew of artists, technicians, and support staff, and we hope you appreciate the amazing work they do.
I'm in.
Kent, did you just open your helmet?
No, that would probably hurt. Just something stuck in my throat. In my helmet. Hey, this is fun. Look at me out here doing this, huh? Come on.
The sensors show no motion or any heat signatures, but I think you should head back to the ship. I'll take over from here.
No. I've got this. You just said there's nothing on the sensors, so let's not get carried away. I've got my blaster. Ugh.
Okay, so you can see we've quite a range of projects that we've worked on. What we're here to talk about today, though, is Spice Frontier. So at the end of that, you would have seen some Spice Frontier shots. So we did a trailer in 2020, and that's what you would have been looking at there. That would have been done in Maya, typical offline rendering pipeline. Whereas Spice Frontier is something that we've been doing in Unreal Engine. And so I'll show you a clip for introducing it.
Imagine a human chef and his alien crew on an epic quest across the universe after the destruction of Earth 250 years ago.
Wait, what?
Chef Kentucky Williams has a dream of astronomical proportions.
Imagine this. Restaurants and food stalls as far as the eye can see.
Kent and his crew aboard the Serrano are traveling through strange alien planets, searching for the lost ingredients of Earth cuisine. His mission is to unite the alien civilizations of the known universe through a shared love of food by recreating humanity's lost recipes. Welcome to the universe of Spice Frontier. This beautifully imagined, visually stunning universe is being developed within a brand new real-time pipeline, leveraging the power of the Unreal Engine. Our team is continuously developing proprietary lighting, rigging, and animation tools that will redefine the creative and technical process of linear storytelling in a real-time environment.
I think some of it got in my suit.
Steamroller Animation is a self-funded studio with a global footprint of more than 230 team members.
Well, it's not too bad. Aside from cosmetic damage, it looks like we just lost an engine coil.
The pilot episode of Spice Frontier has a running time of around 25 minutes and features nearly 400 shots across 9 sequences. Will these spice hunters be able to survive when they themselves become the hunted? Will Kent realize his dream of an Earth cuisine renaissance? Or does his true destiny lie elsewhere?
There we go.
See how the Spice Frontier saga unfolds. Coming soon from Steamroller Animation.
Come on, there we go. Okay, so that's a taste of what the episode is going to be. The project itself, it's meant to be a family-friendly adventure, young adult demographic. It's a very stylized 2D look that we've managed to get out of the engine. It's a 25-minute pilot episode, and it's real time. Some of the things that are important to understand with this is a lot of what you saw there was directly out of engine. So what we did was we got to a certain point with production, and we were looking at the images, and we were going through the normal nuke process where you're sweetening up the images, and so we ended up taking the images back into Unreal and seeing if we could match that look. And we were able to get what we wanted in there, which was really important because what I didn't want was I didn't want to have a rendered out project that is completely different than what you see in Unreal. Because if we wanted to use it anywhere else, whether it's VR or AR or in a game, you want it to look as good as it did in the renders. And so that was what was really impressive was we were able to get the look that we wanted. And as far as the real time part. It was working with the team and convincing them that Unreal is the direction that we want to go in. So the production's been happening for about 2 years, and when obviously it's a big step to be going from a more traditional pipeline and going into Unreal. Oops. Anyways, the real-time part became really important because it, and like I'm sure a lot of you're aware of, being able to get those visuals in front of people, getting everybody on the same visuals, getting lighting happening as early as possible, getting, all the different pieces so that, you can understand and see the visuals, and everyone's on the same page. And so it's really important for us to kind of dive into Unreal and use that as the basis of our pipeline. Because, from my standpoint, real time is sort of where things are going. and getting on board with a tool like Unreal and understanding it and getting your talent pool educated on it and getting them up to speed on it, then it gives us the ability to really make great projects in a timely fashion. And so I will pass it over to David here, and he'll kind of do a bit of a deeper dive for things. There you go.
Thanks, Sean. So kia ora koutou. My name is David Elvey. I'm the CG Technical Supervisor at Steamroller Animation. I've been working with Unreal for the last 9 years or so. And the last 4 years, I've been able to really heavily focus on building workflows specifically tailored to linear content or long-form narrative content. So today we're going to explore the critical question of how do we leverage Unreal Engine to create that linear narrative content. And in this session, we're going to break down some key workflows, including a fundamental problem that we all have to deal with, how we structure Sequencer, the tools that we've developed, and the workflow that it allows us to scale production efficiently. So as Sean showed, the Spice Frontier short has a distinct visual style that has served as the foundation for what we want to achieve. And as you can see from this concept art, our key inspiration was drawn from the aesthetics of classic 2D animated films, where the characters are flat and cel-shaded, while the backgrounds maintain a more volumetric or painterly look. And during production, we faced two primary challenges. The first is nailing the visual style that we had envisioned, and the second was transitioning to Unreal as our core production tool. So before diving into our creative process, let's first address what I believe is a challenge that every studio faces when they want to adopt Unreal Engine for linear content. So on one side, we have traditional CG artists, and these are experts in linear content creation who have a deep understanding of the visual and storytelling demands of animation. And on the other hand, on the other side, we have real-time specialists. So these are people coming from game development with the technical knowledge of Unreal Engine. And we might think that since both sides share common ground, so we're working with models, textures, materials, lightings, and effects, that the transition would be pretty straightforward. But the thing is, this familiarity can lead to a false sense of security, where while the skill set is somewhat transferable, the mindsets and approaches to problem solving can be strikingly different. So I'm curious, does anybody here, would they put themselves into the the game artist circle, coming primarily from there? Not too many. What about the CG artist circle? How many people come from that circle? Yeah, okay. And does anybody think they kind of living in that hybrid world in between? Okay, so a few people. So those people there might kind of have already experienced this push and pull between traditional CG and real-time approaches. But depending on which side of the fence you're on, the way that you approach the same problem might differ quite dramatically. And that brings us to two critical questions that we need to ask ourselves, which is where in production do these approaches or mindsets diverge? And how do we reconcile those differences to create a cohesive workflow? So what we're sharing today is the culmination of wrestling with those opposing forces, the convergence of real-time and linear content. And while the journey hasn't been without its challenges, we've found that embracing this fiction has led to some truly exciting results. Perhaps the most important workflow challenge that we've had to overcome is our shot build process. So when producing linear content, how we work with and structure Sequencer had a massive impact on the entire production. Sequencer forms the core of our workflow in Unreal, and we need to create a stable platform for our Unreal artists to work within. So we can start by looking at the traditional approach for structuring Sequencer Unreal, which generally follows a top-down hierarchy. And typically that workflow might look something like this. At the top, we start with a sequencer representing the episode. Nested within this are scene sequences, allowing us to make high-level adjustments that impact every shot within that sequence. Underneath the scene level, we have sequences for individual shots. And finally, there may be department-specific subsequences, allowing different teams like lighting effects, animation, etc., to manage their respective elements. And this top-down approach makes sense at first. It allows us to create changes at a high level that propagate down through the nested sequences. However, we've found that this system comes with significant drawbacks when scaling. So let's say that we want to work on or render a specific shot. To make sure that we have all the necessary overrides and settings, we need to not only load in the shot, but also the entire scene as part of. And as soon as we load in the scene, we're now loading all of the shots in that scene along with their respective departments. And we found that as you kind of get bigger and bigger, this starts to scale poorly. If we only want to focus on a single shot, we're forced to load in a lot of data from all of these other shots. And this creates memory constraints, slows down the workflow, and limits what we can do within any one particular shot. So what is the real challenge that we need to solve? We need a system that retains the benefits of the hierarchical overrides, allowing us to work at a high level and apply changes across multiple shots, while also minimizing the overhead. The ideal system is going to allow us to focus on individual shots without loading unnecessary data from other parts of the scene. And so to solve this, we developed what we're calling the Shot as King workflow. We've been working with this system for a couple of years, but we have seen other teams and artists beginning to explore similar ideas. So in this system, everything lives within a shot context. We do want to retain the idea of hierarchical overrides, and we still group shots within a scene to an override to be able to apply changes across multiple shots. But here's where our key difference is. Instead of nesting shots inside the override sequences, we nest override sequences inside each individual shot. So here's how that looks practically. Each shot is built in isolation, so at any point we can work on or render it without loading anything else. We continue to use steps to break down the work required for a shot, and this allows different artists to work in parallel. And here we're creating a folder for a particular step, the environment step. Note that we move towards calling them steps instead of departments. One of the great things about Unreal is that it allows our artists to become more generalists and work across departments. So these groupings now become more about the type of work being done rather than the traditional department that is doing the work. Each step has its own set of subsequences for each override, and this keeps workflows segmented and organized. For Spice Frontier, we established two main layers of overrides. We have masters. These are collections of shots that share the same spatial location, and groups. These are subsets of the masters where we group shots that are similar in camera angle or framing. And this allows us to apply broad changes at the master level and then refine them at the group level. We also have a third override, which is just for the individual shot adjustments. And then another issue we had to tackle with this setup is how Unreal handles priority when we have multiple overrides that are affecting the same object. So in the traditional system, priority is determined by the depth of the sequencer in the hierarchy. So the deeper the sequences, the higher the priority. In our new system, however, nesting overrides is going to create conflicts. So instead, we use sequencer's hierarchical bias to manually control priority. So we set the bias of 1 to the master, 50 to the group, and 100 to the shot. And this ensures that changes in the shot override always take precedence, followed by the group and then the master. So by restructuring the workflow in this way, we've created a system that keeps the benefits of the hierarchical overrides while giving us the flexibility to work on each shot in isolation. This shot as king philosophy not only improves performance and scalability, but it makes it easier for our artists to focus on their individual tasks while working in parallel with other artists. So now that we've explored the workflow itself, we can have a look at how we've automated this process with our shot setup tool. So here's a screenshot of Unreal, and we have our tool docked on the right-hand side. The tool is connected to Flow, which is our production tracking solution, and it's fully configurable per project. The main purpose of this tool is to automate the entire shot setup process, and it streamlines the workflow that we just covered, and it does a few extra things as well. So we're going to jump into a quick demo of building that shot. So we're going to set the context to scene 10, shot 200. And once we've done that, we can go ahead and update the sequencer. This will automatically create the sequences, add the necessary overrides, and add the camera actor, followed by what we've discussed with the Shot as King structure. Then we can import the camera animation directly into the shot, and you can see how quickly the shot is built up with everything that's synced up. As the shot evolves over time, artists can continue to update it, and the tool ensures that everything is kept in sync with the data and flow. Because the tool is context aware, it can also handle additional functionality, like in this example, we're importing the camera animation. There's a lot more that the tool can do, and we're going to continue to look into some more of its features a little bit later. So at the start, I mentioned how there are differing mindsets between traditional CG and real-time workflows, and that they brings unique challenges. One of the main conflicts that we had for us was our character workflow. So we're going to move on to have a look at that now and how we solved that problem. So the main challenge here was character versioning. So in Unreal, it's common to import a skeletal mesh once and update it by re-importing the same asset. We keep a single representation. This ensures memory efficiency and animation compatibility. However, in traditional CG animation, rigs often need to evolve as the production progresses. As new shots are worked on, rigs are modified to address specific animation needs. And this creates a challenge. How do we update characters for future shots without breaking or reauthoring animation that has already been approved? We also need to handle variants, which are different representations of the same character. So for example, a character may have a different variant, a default variant, and then a variant where they're all roughed up a bit. Each representation of the character is treated as a different variant, but it's still the same asset. The third element to consider is components. Components are parts of the character that do not require a full variant, but they can be treated separately depending on the needs of a shot. These components are split into separate skeletal meshes and allowing us to have individual control of them during production. But as I mentioned, the most complex of the three was versioning. So to manage this, we created a versioning system that links the two files which are exported from Maya. We have the skeletal mesh file, which is imported into Unreal. This file only versions up when there are structural changes to the skeleton or skinning. And we have the puppet file, or the Maya rig, which is passed to the animators. And this file updates more frequently, and as the rig evolves during production, to accommodate the needs of the new shots. The puppet file contains metadata that tracks the version of the Unreal skeletal mesh that it is compatible. And as you can see, we can have multiple puppet files linking to the same skeletal mesh. So when animators work on their shots, this metadata is embedded into the published animation file. And upon importing, Unreal uses this metadata to automatically assign the animation to the correct skeletal mesh version, ensuring compatibility without the risk of version mismatch. And so to bring everything together, we've developed a custom dynamic character system. So instead of loading all of the character data, the dynamic system ensures that we load into memory only the skeletal mesh assets that are needed. And this improves performance throughout production. The solution keeps our character workflow flexible and fully integrated with our animation pipeline, and it allows us to iterate and update rigs without disrupting previous work. So we're going to circle back to our shot setup tool and see how that automates the process of bringing a character into a scene. So first, the tool checks what animations have been published for the current shot. As part of our workflow, all characters are initially spawned into the anim step shot override. Once we use the setup character buttons, the tool automatically spawns the character blueprint and assigns the relevant animation. So when importing the animation, the tool auto-detects the correct asset and skeleton, ensuring that the animation is assigned to the right version of the character. And so one of the major advantages of switching over to Unreal Engine for linear content is how flexible its systems are, especially when you start combining C++ and blueprints. So I want to talk through how we use both to build elements of our custom dynamic character system. By highlighting a few features and tricks that we used to build this custom workflow, I hope to show how Unreal's can solve this for us. So it might get a little bit technical for artists here. So at the foundation of our character system is C++ class. And this provided the power and flexibility we needed to make the system reactive to data inputs. We're not using C++ for any runtime specific logic, but instead we use it to access some functionality that isn't available in native blueprints. Specifically, we wanted the system to respond dynamically to information that is passed into it. So in our workflow, we use data assets to define asset variants, and each variant data asset holds the version information about that character. These data assets are linked to the character blueprint, which then builds the character dynamically based on the settings provided by the user. When an artist spawns a character, the system needs to automatically generate what variants and versions are available from the data assets, and this allows the user to select valid options for the character. And so to do this, first in our base C++ class, we create some properties. One here we have defined the available character variants, and this is just the T array of that custom data asset that I mentioned. Then we have 2 additional properties that will serve as a drop-down box to select specific variants and versions. And then to ensure these properties can be used in sequencer, we add the specifier into it. Then we create functions for each property that we want to create a drop-down box for. And then on the property, we add the getOptions specifier, and that points to the specific functions that we created. Finally, the function's job is to return a T array of options based on the state of the character, which in turn is going to populate the options in our drop-down box for our properties. And this means that rather than manually typing in a version, artists are provided with an automatically generated drop-down list of valid options. And by using C++ as a foundation, we ensure that all data is accurate and dynamic, creating a reliable technical backbone for our artists to work with. So here's what the property looks like in Unreal when you use the getOptions flag. You get a nice drop-down menu. So with our base system set up in C++, we need to ensure that the characters can integrate seamlessly with sequencer, which is critical for animation and timeline management. Sequencer is designed to work with skeletal meshes, but we want the flexibility of a blueprint system for handling multiple character versions and modular setup. A neat trick is that by making the root component of the class a skeletal mesh component, and then assigning a skeletal mesh asset to it, Sequencer is now going to treat that blueprint like a skeletal mesh asset. And this allows us to leverage all of Sequencer's animation functionality while retaining the functionality of the blueprint system. So once the system's base functionality was set up in C++ and integrated into Sequencer, we could then extend it further with blueprints to make it more user-friendly for our team. And we're going to have a look a little later at some things we did within the blueprint to extend the character system functionality. So now we're going to have a look at our character art style, where we wanted to invoke the classic 2D look. To do this, we settled on a flat shaded aesthetic, intentionally withholding volumetric lighting from the characters to maintain that 2D feel. We start with an emissive material as the foundation. This gave the character a flat cartoon-like appearance. However, to avoid making them look completely flat, we added subtle shadows painted directly into the textures. And this helped elevate the aesthetics while retaining that 2D quality. Next, we enhanced the look by adding directional rim lights. In this shot of Kent, for example, we have 2 rim lights working together. So first we established a directional rim, which uses a modified silhouette offset technique. We then fine-tuned attributes like brightness and color to match the shot requirements. And finally, we control the fade-off by applying a vertical gradient to the opacity. And this creates a smooth termination and taper effect. So we're going to break down the modified silhouette technique, offset technique with this example. You've got a very simple circle. So instead of offsetting the character silhouette to create the rim mask, we instead offset the depth pass and do a depth comparison between the original and the offset. The more we offset, the thicker the rim effect becomes. And here we're also defining the direction of the offset, which controls where the rim is going to appear. So if we now assume that the circle is a depth of 10 and the background is at 10,000, we can sample the depth values. At points where both the original image and the offset are at a similar depth, sort of like in the middle of the circle, we get a very little depth disparity. The depth values are both around 10, so it results in a very small difference. In the top left of the circle, the original value is 10, but the offset is way in the background at 10,000, and this creates a massive positive depth difference. And at the bottom right of the circle, the offset value is 10, but the original is at 10,000. And this creates a massive negative depth difference. After calculating the depth difference, we discard any negative values because these represent depth disparity in the wrong direction. And then finally, we set a threshold and clamp values. Any pixel with a depth difference greater than this threshold becomes part of the rim. Setting the threshold allows the artist to control how much depth difference is needed to determine where the silhouette becomes visible. And by comparing the depth values instead of the silhouette, the system is now also able to include internal edges to the rim as well, not just the silhouette. So here again, we have Kent with the rim applied. And then because our character is using an emissive material, they don't naturally inherit standard shadows from the environment. So to simulate more dynamic lighting effects, we developed the Gobbo system, which allows us to project an art-directable shadow texture directly onto the character. This allows us to precisely control how the shadows behave on the character, adding another layer of visual depth without losing that flat shaded look. So here's the shot in context, and you can see how these different techniques, the emissive material, subtle shadows, rim lights, and Gobbo systems, all work together to create the final look. The characters stand out clearly against the background, yet integrate smoothly into the shot. As we've just mentioned, we have the Gobbo set up to add shadows to our characters. So we're now going to have a look at that system. In this shot, you can see we have shadows interacting with the character. There is a shadow layer indicating the window of the ship, as well as scrolling shadows moving across the characters that indicate movement. These effects are all driven by our Gobbo system, which, as I mentioned, projects painted shadow maps or Gobbos onto the characters to simulate environmental interaction. The system is comprised of 3 components. We have the Gobbo actor, we have a scene manager, and we have our aforementioned character blueprint. The Gobbo actor is placed in the world and defines how the shadow map is projected. It contains a camera component that sets the projection parameters, such as transform, field of view, and aspect ratio. The artist assigns a specific Gobbo texture, such as the window shadow in this case, which is then projected onto the character. Each Gobbo actor is given a unique ID, allowing the system to track and assign specific Gobbos to characters or groups of characters. The character blueprint plays a key role in passing information to the character's material, and it's in the material where we handle the actual shadow projection calculations. So on construction, the character blueprint creates dynamic material instances for the character's materials, which allows them to be updated dynamically. Whenever the Gobbo updates, the camera information, such as the position and the projection settings, is passed to the materials through the character blueprint, and this ensures that the shadows are always accurate and responsive to the movement of the Gobbo actor. Once the data is passed through, the material calculates screen projection UVs based on these projection settings. Finally, we have the scene manager, which plays a lightweight but crucial role. It acts as a persistent bridge that allows the Gobbo actor and character blueprint to stay connected and share information, even when they're spawned dynamically. Without it, the dynamically spawned Gobbo actor and character blueprint won't be able to communicate effectively. So let's have a look at how the material works for this. So here the characters appear without any environment shadows. They look great, but they feel disconnected from the world. So next, the character blueprint passes the camera information to the material, and this generates dynamic UV coordinates based on the Gobbo actor's projection settings. These UVs are updated in real time as the Gobbo actor moves or updates. And here we can see the UV coordinates that are generated for the characters. Once the UVs are generated, these are used to project the shadow texture onto the characters. And here we can see how the shadow mask is applied. Finally, using the ID setup, the Gobbo actor can project to a specific character or across multiple characters. In this case, we have a unique Gobbo actor per character, but one Gobbo actor can be applied to multiple characters if needed. Finally, we can see the shadows fully projected onto the characters, simulating the interaction between the characters and their environment. So that's without the Gobbos. That's with the Gobbos. So the Gobbo system gives us incredible artistic control over how shadows are projected onto our characters. And by dynamically creating UVs based on camera information and allowing real-time updates, we can achieve the stylized 2D aesthetic that we want while still ensuring characters interact naturally with the environment. Like the rim light system, this approach provides both precision and flexibility for art direction. So when working with blueprints in Sequencer, it's important that we understand how properties are set and how that can affect performance and functionality within your blueprints. In our character blueprint, because the character is dynamically built when it spawns, there is a lot of logic that runs to generate the character. The same construction script will run every time a property is updated in the details panel, and that's going to rebuild the entire character from scratch. And while this is fine in some cases, it can become inefficient and isn't really an ideal solution. Additionally, when we expose properties to Sequencer, you might initially rely on rerunning the construction script when these properties change by enabling a setting in the blueprint class called run construction script in Sequencer. While this will ensure that your blueprint reacts to Sequencer updates, it does mean that the entire construction script runs every time a property is changed. Again, not an ideal solution. For example, with our Gobo setup, when new information is passed in, we only want to update the materials related to that change. We don't want to rebuild the whole character. So a more efficient solution is to use blueprint setters. These intercept the property changes directly without rerunning the construction script. And we're going to have a quick look at how that's set up. So first, we want to turn off the run construction script and Sequencer option. Instead of relying on the construction script to update the blueprint, we're going to create a setter function that is called when the property changes. We create a variable and make sure the property is set to instance editable, and also want to set exposed to cinematics. This allows for it to be added to the Sequencer track. Simply exposing the variable isn't enough since we've disabled the run construction script option. So now we need to create a setter function. And setters are common programming techniques used in many languages to control what happens when a property is modified. In Unreal, we can override the default setter behavior to allow us to control how a property is set, and it gives us fine control over that behavior. So now we want to create that function and set some specific settings. The function must be named set with a capital S, followed by the exact name of the variable, and this is case sensitive. So this allows Unreal to recognize that this function is tied to a specific property change. In the function's details panel, we want to tick the call and editor option so that it can be triggered in Sequencer and in the editor. And then we want to create an input for the function that matches the type of the variable exactly. So if the variable we're changing is a float, then this input needs to be a float. The name of the variable here, the input doesn't matter, but the type is very specific. And note that it's important not to add any additional inputs to this function or change the input type, otherwise the setter won't work correctly. Then in the setter function, the first thing we need to do is ensure that the input value is stored into the variable itself. Because we are overriding Unreal's native setter, that is not going to be stored anymore, so we need to make sure we store that value. And after that, you can implement any additional logic that you wish. For example, in our case, we are simply adjusting a parameter on the material instance based on that new value, but you can extend this to any additional functionality that you need. And by using setters instead of relying on the construction script, we gain granular control over property updates. This means that when Sequencer changes a property, only the relevant functionality, so for us adjusting a material parameter, is executed, not the entire construction script. This greatly improves the efficiency of your blueprints in production and is especially useful when working with complex, dynamically built systems like our character setup. So Sean mentioned that one of our goals with Spice Frontier was to adopt as much of an Unreal workflow as possible while still maintaining the unique 2D look. So the last thing we'll look at today is how we use the hybrid approach for our effects, blending traditional 2D hand-drawn animation with in-engine real-time rendering. So here's a shot from the show where we used hand-drawn 2D images for things like the thruster effects and the environment effects. The biggest challenge with this was how do we get our 2D hand-drawn effects sequences into the engine for our Unreal artists to use. For our solution, we created an effects projection system which allows us to achieve this result. So now we're looking at a specific frame of the shot. And our 2D effects were created by some amazingly talented artists in Toon Boom, where each effect was drawn frame by frame. To allow for more control in Unreal, we separate the effects into layers, grouping by elements and depth. These layers are then exported as image sequences, providing flexibility for compositing. To bring our 2D effects into Unreal efficiently, we pre-processed the image sequences into sprite sheets. This ensured that the entire sequences could be represented in a single texture per element, and optimized memory usage and improved performance. A key part of this process was calculating the smallest bounding box that could contain an entire effect on each frame. Using OpenImageIO, we analyzed each frame to determine the minimum space required to encapsulate all the valid pixels. Once the smallest bounding box was determined, we then cropped each image to this region and created a sprite sheet layout. To maintain memory efficiency, we ensured that the final sprite sheet adhered to a power of 2 texture size. And this was a pretty crucial step, as using a power of 2 texture allowed us to optimize the use of texture memory. Doing this means we could leverage bitmaps in the editor for better performance during iteration, while ensuring that the full-size texture was loaded at render time with the highest quality. Without this solution, we found that many of our shots were too heavy to work with, just due to the sheer size and number of the effect sequences. In addition to this sprite sheet, we stored information about how the image was cropped so that it could be accurately replicated in Unreal. Once it's imported into Unreal, we used our custom effects projection tool to align the effects with the camera. This tool converts the screen space coordinates from 2D sequence into 3D space, allowing for depth layering and seamless integration with the 3D environment. Doing this ensured a pixel-accurate projection. Unlike traditional sprite cards, this approach gives us precise control over where the effects sit in the frame or in the screen space without distorting the image. And each layer of the effects can be positioned to the correct depth, maintaining the illusion of 2D animation while blending with the 3D world. So by integrating 2D hand-drawn effects into Unreal with the projection system, we've maintained the traditional look while gaining the flexibility to iterate directly within the engine. And this allows for fast reviews, consistency across shots, and precise compositing of 2D effects in a 3D environment. So where to next? The Spice Frontier project has been an amazing journey where we've had laid a solid platform for building linear narrative content using Unreal. It would be a lie to say that it has been smooth sailing, but I think with this foundation set, we are starting to see the benefits that Unreal has to offer linear content creation. If you want to follow along with the progress of Spice Frontier or any other content from Steamroll Animation, please subscribe to our YouTube channel. We've currently got a series of production diary videos and various other things to check out. The original Spice Frontier short has also been uploaded, so if you haven't had a chance to check that out, go to the channel and you can have a look at that. So that's it from us. I hope you've enjoyed the talk, and thanks from the whole team at Steamroller. I think we have some time for questions.
If anybody had any questions?
Hi, thanks for the talk. Can you talk about